Anything that was protected is going to stay protected because that's the highest level we can do now. And anything that was private in the base class is going to be private in the derived class. We say private in the sense that it is going to be private to the base class. So you can't really use M3 from the player class in this case. If you try to do that, you're going to get a compiler error. Okay, we can also do private inheritance, and the syntax to do that is what you see here. And now private is going to be the highest level we can do in the player class in terms of the members that we got from the base class. So anything that was public is going to become private. Anything that was protected is going to become private. Anything that was private to the base class is going to stay private to the base class. This is what we mean here. But now M1 and M2 just became public to the player class. If anybody else tries to derive or inherit from a player, these things are not going to be accessible. And this is in some way the player class being selfish. It is saying, I am going to get everything I can from my parent class or my base class, but I am going to make it all mine. Nobody else can take this. And this is the kind of setup we can achieve with private inheritance. Okay, so now that we have this in mind, we're going to play with this in Visual Studio Code. We're going to set up a bunch of classes. We're going to set up a person class we're going to be inheriting from. We are going to set up a nurse class, which is going to do protected inheritance. And we're going to set up an engineer class, which is going to do private inheritance. And we're going to really play with this and see how this plays out in real C++ code. So let's do this. Here we are in our working folder. The current project is base access specifier, a demo. We're going to do a demo on this, but before we do that, we're going to grab our template files and put them in place. And we are going to open this little guy in Visual Studio Code by dragging and dropping here. This is going to give us a good starting point. We're going to have our main CPP file. We're going to clean it up and we're going to set up our base class, which is going to be the person class. So let's put this in from scratch. We're going to add our files. We're going to say person h and we're going to say person.cpp. We are going to hop over in our header file and put in our code. Nothing special so far. We have an include guard. We have our person class. It has a bunch of member variables. We have the full name, which is public. We have the age, which is protected. And we have the address, which is private to this class here. This is going to be our starting point. We also have a bunch of constructors. We have a default one. We also have another one, which is going to take all the data we can use to construct a person object. And here we are passing a const string by reference. I think we can fix this and pass a string view. This is going to be better. Let's say string view. And we're going to change the first parameter here to be an std string view by value. This is going to be much better. Okay, we have our class. We can hop over in the CPP file and put in our implementation. We are going to change the constructor a little bit and make sure we are taking an std string view by value. And if you want to type all this code, you can get it from the resource section of this lecture. I am going to attach all the source code and you can download and use this however you want to really make your learning experience as pleasant as possible. So we have our constructor here. It is going to forward the data into our member variables. The full name is going to go into our full name member variable. We're going to grab the age and the address, and we're going to store all this information. We also have an output stream operator, which is going to be printing all this information here. It is going to go through the getters because we have a person object passed as a parameter here, and this is going to work. We can go in the main CPP file and include our person class and create an object of it. We can do something like person1, and we can pass the data that our constructor expects we can pass in the full name, the age, and the address. So let's do that. We're going to say the full name, Daniel Gray, why not? And the age is going to be 27. We can put in whatever we want. And we're going to put in the address. We're going to say Blue Sky Street. You can say 233, for example, and say the number of the house to be 56. Why not? This is a possible address for a person. So we can say person1, or we can use stdcout to print this out because we have an output stream operator for our person class, we can do this. We're going to say person1, and we're going to put him out. And if we build and run this program, we're going to see that this is going to work, hopefully. And we have a problem because we don't have a semicolon at the end of line 6 here. Let's fix that. We're going to run this task to build with GCC. The build is going to be good. We can bring up a PowerShell window, and we're going to use this to run our program. If we say rooster, we're going to see that we have the person printed down. The full name is Daniel Gray. The age is 27. The address is Blue Sky Street 233. And the number of the house is 56. So this is a possible implementation for the person class. But we are really not interested in setting up a person class and doing things with it. We are interested in inheriting from the person class and learn about different kinds of base class access specifiers we can do. So we're going to set up a player class, which is going to inherit publicly from the person class. Let's do that. We're going to put in our player. We're going to put in the header file. Let's say player, not person. And we're going to say player.h. We're going to put in a CPP file. We are going to hop over in the header of player and put in our class. Let's close the left sidebar here so that you can really see everything. We have an include guard in. We have the class player declared. It is going to do public inheritance from person. And what this is going to do is that anything that is public in person is going to stay public in player. Anything that is protected is going to stay protected in player. And anything that is private is going to stay private. So we want to be able to access private data from a person object. For example, we can't access the address member variable here because it is private, but we can use the full name and the age from the derived class. Let's make sure we have a CPP file n before we try things out. So let's hop over to the CPP file and put in a possible implementation. We are going to include person and player because we're going to be using these. And we are going to set up a constructor which is not going to do anything for a player. We also have our output stream operator which is going to print the data. It is going to be using the getters we have in the base class, and we have access to them because we are doing public inheritance. So they are going to be public and we can call them from the outside like we are doing here. Notice that this is an outside player object and we are calling our public members on it, and this is going to work. We also have a destructor n which is really not going to do anything, but we're going to keep it in here because it's not going to hurt. So now what we want to try out is to see if we can access things from the base class. The first thing we have in the base class is the full name, and I think we can actually copy these things, or we can just use them, m full name, m age, and m address. We're going to try and use them in the derived class. So let's try and say m full name and change the full name, for example, to be Daniel Gray or Jon Snow. And we're going to change the age to be 55. Why not? And we're going to try and access the address. Let's see what we called our address member variable. It is m address. We can grab that and use that in our class. If we're trying to access that, we're going to get a compiler error because that's going to be private to the base class. You notice that if we even try to put some junk data, we're going to have a squiggly line because this is not accessible here. And Visual Studio Code is going to say that this is not accessible because it is private to the base class. So we can access m full name because it was inherited as public. So this is going to be okay. We can use age because it was inherited as protected. We can use it in a derived class, but we can't use the address because it was inherited as private and it is private to the base class. So this is not going to work. Even if we try to compile our code, we're going to get a compiler error. Let's try to do that so that you can really see for yourself. Okay, so we have a compiler error, and this was declared in the base class as private. This is what the compiler error is saying. So we shouldn't really be doing this. The derived class has no business modifying a private member of the base class. This is the message here. So we're going to comment this out and say that this is going to give you a compiler error. But we are also going to create a player object and try to access these guys and see how access is from the outside. So we're going to go in the main CPP file and we're going to include player.h and we're going to create a player object. We can put in a separator and say a bunch of dashes here. This is going to do, I think this is going to work. And we're going to create a player object. We can say player and not put any parentheses here. This is going to call the default constructor that we have in our player class. And we can try to use this. But before we do, let's try and build and see that this is going to build just fine. We're going to build with GCC. Let's do that. We're going to see that the build is good. We can try and access stuff from this player object. We can say player and say m full name. You see that this is accessible. We can actually change this to Samuel Jackson. We can do that. But if we try and say player mh, we're going to see that this is not accessible here because this was inherited as protected. If we go back to person, we're going to see that the age is protected. So it will be accessible in derived classes just like we did in our play method of the player class. But we can't access the age from the outside of a player object because that's not going to be accessible from the outside. This is a defining feature of the protected access level. So this is not going to work. Even if we try to build, we're going to get a compiler error along the lines of this is not accessible in this context, and it was declared in the base class, so we can't really access it from the outside. This is the compiler error here. So we're going to comment this out and say that this is going to give you a compiler error. Okay, so I hope you know that you can't even have a chance accessing a private member of a base class from a derived object in the main function like we do here. So if we try and do player and say m address, this is not going to work. Okay, so if we try to change this, for example, to some junk data, this is not going to work. We're going to get a compiler error because this was declared private in the base class. And it is private to the base class. You can't really access it from the outside. You can't even access it from a derived class, so let alone access this on the outside in the main function. So this is not going to work. It is going to give you a compiler error, but we're going to build and show you the compiler error because we are learning here. So we're going to get a compiler error that says m address is private within the context where we are trying to use it. So we can't really use it from the outside here. Again, this is going to give us a compiler error. Let's say that here. And this is really what I wanted you to learn about public inheritance. Anything that is public in the base class is going to be public in the derived class. Anything that is protected is going to stay protected. And what that means, it will be usable in the derived class, but you can't use that from the outside. And anything that is private in the base class is going to stay private. So you can't use that from the derived class, and you can't even use that from the outside like we are doing in the main function here. This is not going to work. Okay, so now that we have this in place, we're going to set up another class that is going to do protected inheritance, and that's going to be our nurse class. So we're going to put this in. Let's put in a nurse header file. This is going to be nurse.h. We're also going to put in nurse.cpp. Okay, so we're going to head over in the header file and put in the code for our nurse class. We're going to say class nurse and say protected to mean that we want to do protected inheritance. And what this is going to do, anything that is public in the base class is going to be protected in the derived class, which is our nurse class. Anything that is protected is going to stay protected. Anything that is private is going to stay private to the base class. This is what we mean here. Okay, now that we have this in, we can put in the implementation for our nurse class. And we're going to have a constructor, and we're going to have our output stream operator, and we're going to have a destructor, which is really not going to do anything because we don't have any dynamic memory allocation in our class. We are going to try and build this code to see that it is going to work. We have a squiggly line in the main CPP file, but it was because of the line 15 here, and it has been commented out. Let's see if we can build this program. Okay, you see that the build is going to be good, and we are able to call thanks from our output stream operator. You see we have a nurse operand. We are able to call this get full name and get age member function because they are now protected in the nurse class, but we are able to call them from the outside because this operator is a friend of our nurse class here. I want you to say this. Some of you are going to ask, aren't we using an object and calling a method using the dot operator? This qualifies as calling things from the outside. And yes, that's true. But this method is really like a member function in that it has access to private and protected data from our nurse class. And the reason is it is a friend of the nurse class here. That's why we are able to do something like this. But what I really want you to see now that that doubt is cleared is the kind of access we have to things from the base class. We will still be able to use m full name here because it was inherited as protected. So we can use it from a derived class. We can say m full name Jon Snow. This is going to work because this was inherited as protected. Now it is protected in the eyes of the nurse class. This is what we mean here. So this is okay. This is going to work. We can get the age. We can use that. And we can say John's. And we can say 23, for example. This is going to work because this is protected. But we can't use the address. If we do that, we want to be able to change it. We will get a compiler error because this is private to the base class. This is the same thing we saw in the last lecture. This is going to give us a compiler error if we try to build this program. Let's try and build it to really prove this. The build is going to be good without line 17 here, but if we uncomment it and try to build the program, let's do that. We are going to get a compiler error, and the compiler error is going to say, let's go up and see if we can get this message. It's going to say, M address is private within this context where we are trying to use it. And that's line 17 of the nurse class. If we go there, we're going to find the offending line here. So we're going to comment this out and say that this is going to give us a compiler error. Okay, so you shouldn't do this. Now that we know things from the inside, let's see how things fare on the outside. We are going to hop over to the main CPP file and include our nurse class. And we're going to create a nurse object. We can go down and say stdc out, and we're going to put in our dashes, and we're going to create a nurse object. I think we have a default constructor for a nurse. We're going to say nurse1, and we're going to basically try and do the same things we did for the player object from the outside. If we try to access the full name, now it's not going to be accessible because it was inherited with protected access level. So if we do nurse and say m full name, you're going to see that autocomplete is not here. This is a good sign that this is not accessible from this place. If we say Davy Jones, we're going to get a compiler error. And if we try to build, we're going to get a descriptive compiler error. At least I hope. So let's build. We're going to see that we build with errors. And if we go up, we're going to have our error. Nurse was not declared in this scope. Did you mean nurse 1? Yes, we meant nurse 1. Sorry for that. We're going to build again. Thank you, GCC, for pointing this out. We are going to get another kind of error. And if we look at our error here, we're going to see that m full name is inaccessible within this context because it is a protected member of the nurse class now. It was inherited as protected, and we can't access it from the outside. We can access that from the inside because it is protected. But if we try to access it from the outside, we're going to get a compiler error. And this is a defining feature of protected inheritance. Even things that were public in the base class are going to become protected in the derived class. So this is the message here. And this is going to give us a compiler error. Okay, so if we also try to access nurse1 and say m age, this is also going to give us a compiler error. Let's try to put in an age here. Let's put in 51. You're going to see that we're going to get the same kind of error. Let's really try these things out and learn about every possible way we can set up these things. If we look at the error, we're going to see that image is protected within this context, so we can't really access it. So this is the compiler error we get. And I hope you know that if you try and access the address, you're also going to get a compiler error because that's private to the base class. So we can't even use that from a derived class like nurse here. That's not going to work. Let's say that here we have a compiler error and we're going to set up another class which is going to inherit privately and see how that works out. The class is going to be engineer. We're going to see that the error here goes away. So let's create our engineer class. We're going to put in a header file. That's going to be our engineer.h. We are also going to put in engineer.cpp. Okay, so we're going to hop over to our header file and put in our engineer class. We're going to say engineer and say that we want to inherit privately from the person class. This is the syntax here. And this is going to do private inheritance. And what this means is that anything that is public is going to become private to this class. Anything that is protected in the base class is going to become private to this class. And anything that was private in the base class is going to stay private. We want to have access to that whatsoever in the derived class directly. We are going to hop over to the CPP file and put in our implementations. We're going to have a default constructor for engineer, which is not going to be taking any parameter. We're going to have our output stream operator, which is going to still work because it is a friend of the engineer class. So all these things that were inherited to be private are going to be private to the engineer class. And any friend of the engineer class will have access to that. That's why we are able to call get full name, get age, and get address here and get these things to work. Okay, now that this is out of the way, we can try and access our things. We're going to try and do the same things we did in our nurse header. We're going to copy the code because we are trying to access the same member variables. And we're going to see how this fares in our engineer class. This is going to save us a few seconds. If we try to access the full name, this is going to work because it is private to this class. If we try to access the age, this is going to work because all these guys are now private to this class here. But if we try to access the address, this is going to give us a compiler error because address is private to the base class. If we go back to person, we're going to see that this is the case. And if you try to inherit from this class in any way, you're not going to be able to change this access level. This member variable is always going to stay private to the base class, and no derived class will be able to modify or read from this in any way. So this is the setup we have here. If we try to build, we're going to get a compiler error. Let's first take this out and show you that this is going to build just fine without this line here. And I am going to build again and show you that if we bring that in, we're going to get a compiler error. So the build is good. We can go back in our engineer class and bring in the offending line. We can uncomment this. And if we build, we're going to get a compiler error. Let's make sure you see the compiler error here. So the build was finished with errors. And if we go up, we're going to see that we have an error here. And the error is going to say M address is private within this context. And the context is what we have at line 17 in the engineer class. So we can go there and find the offending line. And we're going to comment this out. And this is going to give us a compiler error. Now you know this. But this is how things are going to work from the inside. But we also need to look at how things fare from the outside. Let's go back in our main CPP file. We are going to include our engineer class, and we are going to create an engineer object. We can go down and say stdc out and put in a bunch of dashes to separate our things. And we can create a engineer object, and that's going to be engineer1. And if we try to access the full name, that's not going to work because it is now private to the engineer class. If we say engineer1 and try to say M full name and try to change the name in any way and say, for example, Olivier Godson. I am making this up. I don't know if this name exists. But the point is that this is not going to work. It is going to give you a compiler error because M full name is now private to the engineer class. It was inherited to be private to the engineer class. And if you try to do this, you're going to get a compiler error. Let's try and build with GCC to really show you this. And the build is going to be finished with errors. And if we go up, we're going to find our error. Full name is inaccessible from within this context. And the offending line is at line 27 of the main CPP file. If we go there, we're going to find our line and we're going to say that this is going to give us a compiler error. So let's say that. And we can't even access the age and the address member variables. The age is also going to be private to engineer, but the address is private to the base class. So that's not going to work either. So we can't really access that from the outside because it is now private to the engineer class. So let's go down and really show you that. We're going to go down and say engineer1 and say M age. If we try to do that, that's not going to work. That's going to give us a compiler error. And if we try to build, we're going to get a compiler error along the same lines as what we just got here. The build is going to finish with errors, and if we look at our error, we're going to see that M age is protected within this context, so we can't use it at line 28 of the main CPP file. This is going to give us a compiler error. Let's do that. We're going to say that here, and if we try and access the M address member variable, that's not also going to work because this is even more restricted for access. It is private to the base class, so we can't access it from a derived class directly. We can't even access that from the outside, so you should really know this. So if we put in some junk data here and try to build, this is going to give us a compiler error that says that this is not accessible from the main CPP file like we are trying to do on line 29 here. So we're going to get an error, and the error is going to say M address is private within this context. And the offending line is at 29 of the main CPP file. We're going to take this out and we're going to say that this is going to give us a compiler error. This is really all I wanted you to see in this lecture. And before we wrap this up, let's try and build again and make the error go away, because I don't like to leave you with code that has compiler errors and the build is good. And this is really all I wanted you to see in this lecture. That you can do all kinds of inheritances in your C++ code. You can do public inheritance, you can do protected inheritance, you can do private inheritance. And we had a chance to look at all these scenarios in this lecture here. The message is the same as we saw in the last lecture. If you do public inheritance, anything that is public in the base class is going to stay public. In the derived class, anything that is protected is going to stay protected. Anything that is private is going to stay private. And this is really misleading in a way. The private data from the base class is not going to be private to the derived class. It's going to stay private to the base class. So if you try to use this in any way from the derived class, you're going to get compiler errors because you can't access that, even if it is part of you. Player has a person part of it, but it can't access private members from the base class. You should really know this. We have seen that we can also do protected inheritance, and that's going to constrain things to have the highest level of access to be protected. So anything that is public is going to be stripped down to protected access. Anything that is protected is going to stay protected. Anything that is private is going to be private to the base class. You should really make this super clear. We can also do private inheritance as we saw, and this is going to strip down the highest level access to be private. So anything that is public is going to be constrained to be private. Anything that is protected is going to be inherited as protected to the player class. But anything that was private in the base class is going to stay private to the base class. Even the player class won't have access to this member directly. If we really need access to private data from the base class, we might go through public getters or anything we get from the base class, but we can't access M3 directly and use it from the derived class. That's going to give us a compiler error. This is really all I wanted you to see in this lecture, and I hope you find this interesting. We are going to stop here in this lecture. In the next one, we're going to try and zoom in on private inheritance and show you some things you really need to be careful about. So go ahead and finish up here and meet me there. In this lecture, we're going to zoom in on private inheritance. And we're going to see that the class that does private inheritance is really selfish. Here is a simple structure we will be using in this lecture here. We will set up a person class which is going to act as our base class. We are going to inherit from this class privately and create an engineer class. And what this is going to do, it's going to take everything from the class person and make it private to the engineer class. So the M1 member variable, which was public in the base class, is going to be private to the engineer class. This is what we have here. The M2 member variable, which was protected, is going to become private in engineer. That's what we have here. And the M3 member variable, which was private to person class, is going to stay private to person in the eyes of engineer. This is the situation we have here. So the problem is going to really show up when somebody else tries to inherit from engineer. Because M1 and the M2 are now private to engineer, they will be inherited but still inaccessible to the civil engineer class here. M1 and M2 will be private to the engineer class, but M3 will be private to the base class, which is person. So hopefully you can see the message that if a member variable is private, it can't be inherited in any way. It doesn't matter which kind of inheritance you do. So starting from engineer, which has made M1 and M2 private to itself, it's no longer possible to forward these guys down in the inheritance hierarchy. Another way to look at this is to see that the engineer class is really selfish. It is saying, I am going to take everything I can get from my parent classes because I am inheriting privately, but nobody else will be able to take things from me because I'm going to make them private to myself. So even if civil engineer is doing public inheritance, that's not going to give him any access to these member variables, which are now private to the engineer class. Hopefully you can really see this. And private inheritance is going to really constrain what you can forward down to other classes that are going to be inheriting from you. This is the message I am trying to convey here. Okay, so here is the same example in code. We have our person class. It's going to have our member variables. We're going to have the full name, the age, and the address. They are going to have public, protected, and private access. We are going to inherit from person and create our engineer class. We are going to privately inherit from person, and this is going to take everything we got from person and make it private to the engineer class. And one exception is going to be what was already private to the base class, which is our person class here. This is going to still stay private to the person class, regardless of what kind of inheritance you do from person. But any other thing, if we have any member variable which are public or protected, or even if we have some member functions which are public or protected, everything is going to be private to the engineer class because we have done private inheritance here. So if we inherit from engineer and do any kind of inheritance, we are going to do the most relaxed kind of inheritance, which is going to keep the kind of access we had in the base class, but this is not going to improve anything. Everything is going to stay private to the engineer class. And the civil engineer is really not going to have any access to any member variable or member function that is inherited from the engineer class. And we are going to see this in a minute when we hit Visual Studio Code. So again, if a class is doing private inheritance, it's really another way to say this class is selfish. It's going to take everything it can from the parent class, but it's not going to forward nothing to downstream inheriting classes. And this is the setup I really want you to understand here. And only do private inheritance when you want this kind of behavior. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is closing in on private inheritance. We're going to zoom in on this and really understand the effects of doing private inheritance. We're going to grab the code from the previous lecture, and we're going to grab the engineer and the person class. These are going to be our starting point here. Make sure you grab the .vs code folder if you are using VS Code with this course. That's going to give you the basic settings we need to do our C++ program. I am going to copy these guys down and put these in our current project. And again, make sure you have the main CPP file, the person class, and the engineer class. And these are going to be our starting point. So we're going to open this little guy in Visual Studio Code by dragging and dropping here. We're going to look at our main CPP program. We are not going to include nurse because we don't have this included here. And we can really take out everything we have in the main function. We're going to be adding our own thing here. We also don't need the player class here. We're just going to be using person and engineer. Let's look at the person class. It is going to have the member variables that we expect. We are going to have a public member variable, the full name, a protected member variable, mAge, and a private member variable, maddress here. We are going to create an engineer class, which is going to privately inherit from person. So it is going to make everything private to itself. The engineer class is going to have a person part in it, but the member variables we get from the person class are going to be stripped down to private access level, except for the member variables which are already private in the base class, and that happens to be the address. So it doesn't matter which kind of inheritance you do, the maddress member variable is going to still be not accessible to inheriting classes. This is going to still be private to the base class, which is the person class here. So the full name is going to be stripped down to private access level in engineer. The age is also going to be stripped down to private access, and these are going to be private now to the engineer class. And any class that tries to inherit from engineer is not going to have access to these guys. So if we do any kind of inheritance from engineer, we want to have access to full name, we want to have access to mAge, because these are going to be private to this class here. This is the setup we want to understand in this lecture. So what we're going to do, we're going to set up a new class which is going to inherit from our engineer class, and it is going to do public inheritance, and we're going to see how this works. We're going to create a civil engineer class which is going to inherit from engineer. So let's do this. We're going to create a header file for our civil engineer class, and we're going to create a CPP file. We are going to head over in our header file and put in the class. It's not going to be anything sophisticated. We're just going to have in our include guard, we're going to create a civil engineer class, which is going to publicly inherit from engineer. But remember, everything was made private to the engineer class. So even if we're doing public inheritance, the full name member variable is going to be private to engineer, the age is going to be private to engineer, and engineer won't have any access to these guys. But before we really play with that, we're going to put in our implementation in the CPP file. So let's put in the code here. We're going to put in the implementation, and we're going to have our constructor in place, but notice what happens on our output stream operator. The output stream operator is a friend of the civil engineer class, so it should have access to anything we have in our civil engineer class. But notice what is happening here. The getFullName method is not working because it has been made private to the upstream class, which happens to be our engineer class. And we can't really access them, even if we know that they are really part of the interface of the person class. We have them as public members of the person class. But when the engineer class did private inheritance, it made everything that is not private to person private to itself. So these getters are going to be private to engineer when the engineer does private inheritance. The member variables, which are public and protected, all these things are going to be stripped down to private access level. So they are going to be private to engineer, and any kind of inheritance you're going to do is not going to change that. They are going to be inherited as private to the engineer class. That's why we can't even call them from a function which is a friend of our civil engineer class. And we know that if you mark something as a friend, it's really going to have access to anything you have, including private members. But we can't call any of the members from the engineer class because everything is now private to the engineer class. This is what I want you to see. If you do private inheritance, this is going to really strip down anything from the upstream class and make that private to the class that is doing private inheritance. This is the message here. And again, if you go in any method of the civil engineer class and try to do any kind of access, for example, calling the get full name method is not going to bode well. We're going to see that this is inaccessible here. If we try to access m full name, for example, change this to be something else, let's say Daniel Gray, this is not going to work. If you try to access mh and change it to 45, for example, this is not going to work. We already know that the address is private to person, so we shouldn't really try to access it because it is inaccessible regardless of any kind of inheritance you do. But the members that were public from person can't be accessed from any class that is inheriting from person, even if we know that these things are public or protected in the person class. And this is really what I want you to see. If we try and build our program, we're going to get a bunch of compiler errors saying that we can't access these guys from our civil engineer class. We are going to use the GCC compiler here because it is our favorite. And we're going to see our compiler errors here. Okay, so we're going to get a bunch of errors. Let's go up and see all of them. We're going to get an error saying that get full name is inaccessible within the context of the civil engineer header class at line 13. We are calling this method. That's not going to work. We have another error here saying that the get full name method is not accessible from line 13 of the civil engineer header. Okay, it is really the same error, but if we go down, we see that we get a bunch of other errors. We have m full name, which is not accessible. We have mh, which is not accessible. We can't really do these kinds of things from the civil engineer class because all these are going to become private to the upstream class that did private inheritance. So let's take these out and show you that even if we can't access these guys, they are still part of our civil engineer class, and we're going to use a debugger to do that. I am going to take out these things, or I can comment them out and say that they are going to give you compiler errors. I think this is going to be more descriptive. So let's say compiler error, and access to the edge is also going to give you a compiler error. And we're going to go down and show you that we're also going to have the same problem in our output stream operator. So if you really want your output stream operator to work here, what you can do is put some public members in the engineer class and make it give you access to the members that were eclipsed to private access in this class here. For example, you can return the full name. You see that we can access that here. You can return the age, but you still don't have access to the m address member variable because this is private to the person class. But I really don't even want to do this because doing this kind of design is sign of bad design in the first place. So if you need to do those kinds of getters and forward them down to inheriting classes, why not change the design in the first place and not do private inheritance here? For example, if you change this inheritance to protected or public, these members are going to be directly automatically forwarded down to any inheriting class. So just know that you can put in public getters that are going to give access to the full name and age, but you still won't be able to access the address member from the inheriting class, because this is the design you achieve by marking something as private in the base class. If you want the address to be forwarded down, you might change the access level we have here and maybe make it protected or public. So this is the ideas I really want you to grasp. I am going to comment out the offended code here because I want you to be able to build this program and see that even if we can't access this get full name and get address members from inheriting classes, they are still part of our interface. We just can't have access to them because of the choices we have made in upstream classes. So what I am going to do, I am going to go in my main CPP file and I am going to create an engineer object. I will also include civil engineer here. Let's do that. And I am going to create an engineer object, and I am going to create a civil engineer object. And I am going to just say done here. And I am going to put a breakpoint on line 12. We are going to use a debugger to really see that engineer objects and the civil engineer objects still have a person part of them. We just can't access the interface that was eclipsed by the engineer class. So we are going to hit the run tab here, and we are going to start our debugging session by clicking on the green button here. We are going to build our program, and if the build is good, we're going to plug the binary that was generated into our debugger, and we are going to hit our breakpoint in a minute. Once we hit our breakpoint, we are going to look at the local variables we have in the main function. We're going to see them on the left here. If we expand, we're going to see that we have an engineer1 object, and we have a civil engineer1 object. If we look at our engineer, we're going to see that we have a person part of this, which is our base class. And if we look at civil engineer, it's also going to have a base of engineer. So any civil engineer is also going to be an engineer, but the engineer part of civil engineer also has a person part of that. You should really see this information. And the main message I want to convey here is that all these objects have a person part of them. We just can't access that part in objects of our inheriting classes because of the design decisions we have made. Let's close this off now that you have seen this. And again, we are really working on this inheritance hierarchy. The base class is person, and it's going to have these member variables. But if we do private inheritance from the person class, anything that is not public is going to be eclipsed down to private level access. So any other class that is going to inherit from our engineer class now is not going to have direct access to these members because they are going to become private to this class here. And that's the experience we have if we try to use any of these methods and members we get from engineer. This is not going to work because they are now private to the engineer class. This is the message here. So the get full name, get age methods are not going to work if we try to use the contract count member, which comes from the engineer class. That's not also going to work. If we look in our header and try to use any of these members, we're going to get compiler errors because all these guys are now private to the engineer class. This is really all I wanted to share in this lecture. Let's head over to the CPP file and comment this out again because I don't want to leave you with these compiler errors. I hope you found this lecture informative and fun. We are going to stop here in this one. In the next one, we're going to see that we can actually resurrect some members back in scope if they were eclipsed by the kind of inheritance we did from an upstream class. Go ahead and finish up here and meet me there. In this lecture, we're going to explore how we can resurrect members back in scope. So what do we mean here? Suppose we have our trusty inheritance tree here. We have a base class person. The engineer class is going to do private inheritance, and it's going to really be selfish and say, I am going to take everything I can from the upstream person class, but I am going to make everything my own, and nobody inheriting from me will have access to these guys. For example, M1 and M2 are going to be private to the engineer class starting here when the engineer class does private inheritance. So any other class, for example, civil engineer, which is inheriting from the engineer class in any way, won't have access to the M1 and M2 member variables. So suppose for some reason that we have this kind of setup here. But again, we want some members to be accessible to other downstream classes. Suppose, for example, we want the M1 member variable to still be accessible to downstream classes while we have done private inheritance. C++ is really weird in a way. It is going to work hard to really prevent you to do things and then give you a backdoor you can go through to allow the same thing you were trying to avoid in the same place. It is the same kind of logic we have here. It allows you to use private inheritance to prevent downstream classes to access to anything you got from upstream classes. But then again, it allows you to change that and relax the access to downstream classes. For example, we can change the access of M1 and M2, make it more relaxed, make it public or protected if we wanted that. So let's take a look at some code because I know that these things can really be confusing. Okay, we are going to start from a person class, which is going to have a bunch of member variables. We will also have a bunch of getters that are going to return all these member variables. And we are going to do private inheritance from person in an engineer class. This is going to strip down access to the members we get from person to private level access. For example, the get full name member function, the get age, the get address member functions are going to be private to the engineer class now. But for some reason, you might want to redirect them to a more relaxed access level. And you do that using the using keyword. So the first thing you need to do is to choose the section in which you're going to be putting these using statements. For example, because we put them in a protected section, all these guys are going to be resurrected with an access level of protected. If we put them in a public section, they are going to be resurrected with a public access level, and they are going to be accessible from inheriting classes. One thing you should know is that you can't resurrect something that is already private to an upstream class. For example, we know that our maddress member variable was private to the person class, so we can't really resurrect that in an inheriting class. If we do that, we're going to get a compiler error. And hopefully this is going to drive the point home that private inheritance is really, really serious in that it's going to strip down access to private level access in an inheriting class, and any downstream inheriting class will never be able to resurrect those member variables to a more relaxed access level. So because everything here is inherited as private by default, any downstream inheriting class will never be able to resurrect these guys, for example, to public or protected scope. This is the message here. And you can use this kind of design if you want that. But personally, I don't like to do this because it's going to make your code much more hard to read and understand. If you want these guys to be public or protected, why not make them public or protected in the first place and really not use private inheritance? That's going to be much more direct to see and understand, and your code is going to be easier to work with for you in the future or for some other developers that will get to work on your code in the future. So this is the message here. You can use this feature to resurrect members back to a relaxed access level. And now that you have an idea about this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is resurrecting members back in context. We are going to completely reuse the code from the last lecture because it's going to give us a good starting point. We can copy everything except for the binary here. We don't need that in our current project. We're going to put in our starter code and we're going to open this little guy in Visual Studio Code. So we're going to have our code, we're going to have our main function, And we're going to have all these objects created here. I'm really not sure if we're going to need this yet. So let's take this out. And we're going to look at our person class. It is going to have our members here. And we are going to have a bunch of getters, which are going to be returning these member variables. And we have a constructor here, which is really going to build a person object. Nothing complicated here. We have an engineer class, which is going to privately inherit from person. And we know that this is going to eclipse everything that is not private in the person class to private level access. So everything is going to be private to the engineer class now. But sometimes we don't want to do that. For example, if we go down in our civil engineer class, we're going to see that the getFullName and the getAge methods are going to be private to the upstream engineer class. And that's going to break the code for our output stream operator. And it's not going to work because we want to have access to getFullName and getAge. And that's also going to kill access we had on the getAddress method, which would give us access to the address member that we have in our person class. Let's make sure we are looking at person. I am confused here. We have a lot of pieces of code here. Where is the person header? It is down here. So we have the getAddress method, which is going to return the address. We want to have access to that in our civil engineer class to be able to print all this information. If we also want to print the contract count, we can go in our engineer class and put in a method which is going to return that. So we can say int and say get contract count. And this is going to be a const member function because it's not going to be modifying our object. We're just going to return a value. We're going to return contract count. And we can go in our civil engineer implementation file and change this to say operand get contract count. We can do that. Okay, we have this method now. We want this to work. This is going to work because we are doing public inheritance from the civil engineer class, but we want this to work. We want getFullName, getAge, and getAddress to work here. And we can use the using feature to resurrect these members to an access level, which will allow our civil engineer class to pick them up. So we can go in our engineer class and set up, for example, a public or protected scope. We're going to use protected because we want these to only be accessible from inheriting classes, for example. So we're going to say protected, and we're going to say using. This is the syntax. We're going to say person, and we're going to say getFullName. We're going to say using person getAge. We're going to choose this, and we are going to say using person and say getAddress. I think we have that method here. The moment we do this, we're going to go in our civil engineer class. You're going to see that it is going to work now because what we just did is resurrect these members to have protected access level in the engineer class. So the inheriting classes are going to look at this and see that they have a protected access level in the engineer class, and they are going to be forwarded down to any inheriting class. We could also change this to public. This is also going to work. They are going to be inherited as public. And hopefully you can see that any member that you resurrect is going to take the access level of the section where you resurrected. If we resurrect them in a public scope, they are going to be resurrected with a public access level. If we resurrect them in a protected scope, they are going to be resurrected with protected access level, and this is the message here. Now, if you happen to have a bunch of overloads in an upstream class, for example, suppose we have a bunch of add functions in the person class, we can go in and put in, let's do that. We can go down and say double or int, let's say int. So that's going to be much simpler. We can say add and say int A and say int B and say int C. We're going to have three things that we are adding. This is going to be a const member function. It's not going to be modifying our members in any way. So we're going to return A plus B plus C. This is something we can return from a member function here. And we're going to do an overload of the add member to do the addition of two parameters. So we're going to only have A and B, and I think we can use A and B in the first overload here, that's going to be much easier to follow. So we have one that adds 2 parameters, and we have another one which is going to add 3 parameters. If we privately inherit from person, these guys are going to be stripped down to private level access in the engineer class, and they won't be accessible from in any other downstream class. So for example, if we head over in our civil engineer class and try to say add 10 to 2, for example, we're going to get a compiler error because we don't have access to this. But we can also resurrect these add members in our engineer class. So let's go there, and we're going to set up a public section in this class here, and we're going to say using person add. This is going to resurrect all the overloads that we have in our upstream class. And this is going to be the case because we resurrect only based on the name of the function, and the same name for a member function can be shared by many overloads. So if we do this kind of resurrecting, we are doing for the add member function from person, we are going to get all the overloads. If we go in civil engineer, we will be able to use the member function taking 2 parameters. We will also be able to use the one that takes 3 parameters. They are all going to be resurrected here. This is the message I want to convey. If we do this, you're going to see that this is going to work, and our code is going to just build fine. Let's build and see if the build is good. Actually, we're going to pass this through GCC. The build is going to be good, so everything is working just fine. And the message I really wanted to convey is that it is possible to resurrect members in a more resurrected access level if you are inheriting using a really constrained base class access specifier. For example, we are inheriting using a private access specifier. This is going to eclipse everything we get from the upstream class to private level. But if you think that's too much and you have a few members that you would like to put in a more relaxed access level, you can use this resurrecting feature, and it is going to make things accessible in downstream classes if that's what you want in your program. And again, I hope this drives the point home that C++ is going to sometimes work really hard to prevent you from doing one thing, and then again give you a backdoor you can go through to do that same thing. This is the same thing here. We are doing private inheritance, but we are allowed to kill or relax the effects of private inheritance by bringing things in a more relaxed access level. And you can use this if it makes sense for your code. Again, I don't like this personally because it's going to make code confusing. If other developers see that you are doing private inheritance, they are going to expect everything from the upstream class to be private to the class that is doing private inheritance. And if they see that they can use these things that should be private by default in downstream classes, this is really going to confuse them, and it is going to cost them more minutes to look at your code to really understand what is going on. So if you really want these things to be accessible in downstream classes, why not do public or protected inheritance in the first place? This is my argument here, but it is going to be your choice. My job here is to make you aware of the possibilities that you have in the C++ programming language. Okay, the last thing I want you to see in this lecture is that if there is something that was already private in an upstream class, you can't resurrect that. If you try to do that, you're going to get a compiler error. This is also going to drive the point home that you can also resurrect member variables. So far, what we have only resurrected was all member functions, and we can also resurrect member variables. So we're going to try and resurrect the maddress member in the engineer class, and let's see how this works out. So let's go in our engineer class. We can go in our protected section. We can do this really in any kind of section. We're going to say user, and we're going to say person, and we're going to say maddress. You see that this is not going to be available in autocomplete. This is going to be a sign that this is going to give us a compiler error. And if we try to do that, we're going to see that we're going to get a compiler error. The message here is that if something is already private in an upstream class, you can't resurrect it. It is eclipsed down forever. And hopefully this drives the point home again that private inheritance is really serious. For example, in our civil engineer class, we can't resurrect something that was already eclipsed to private level access by the engineer class. Let's go in our person class and see if we have any other member function we can play with. We're going to put in a member function that says do something. We're going to say void do something, and it's going to be const. It's just going to say hello. We can do something like this. We are learning. And this method is going to be eclipsed down to private level access because we are doing private inheritance from person. Let's go back in our engineer and comment this out because it is going to give you a compiler error. If you build, you're going to get a weird compiler error. I think I should really show you this because we are learning here. So we're going to try and build our program anyway. We're going to pass this through GCC and we're going to see the kind of compiler error we get. And we are going to see that there's no member std. This is a problem we just introduced in our class here. I think to solve this problem, we can just put our definition in the CPP file. We can do that. We're going to grab this and we're going to put the definition in person.cpp because we have IO stream included in there. This is going to make our code work much better. Let's do this. We're going to say void and say person, and we're going to say stdc out hello. This is going to fix our problem here. And the only problem we will have will be in engineer, where we are trying to access things that are now private to the base class. Why do we have this squiggly line here? Let's take out this and try to build, really make sure that this problem is not existent. And it was Visual Studio Code messing with us. So we're going to bring this in and build, and we're going to see the kind of compiler error we get here. This is what I am trying to make you see. You see the build is finished with errors. If we go back, we're going to see that string person m address is private within this context. We can't really resurrect it. If we do this, we're going to get this compiler error here. This is the message. You shouldn't really try to resurrect something that is already private to an upstream class. And that's what we are doing here. We are trying to resurrect a member which is private to person, and this is not allowed in C++. If we do that, we're going to get a compiler error. Okay, so, but what I want you to see here is that a public member which was in the base class was also eclipsed down to private level access in engineer. So if we try and resurrect the do something method in our civil engineer class, we're going to get a compiler error. So let's try and do that. We're going to put a public section. Why not? And we're going to go down and say using person. And it say do something. We have this method here. But if we do this, we're going to get a compiler error because this method is now private to the engineer class. And why is it private to engineer? Well, engineer is doing private inheritance. That's going to eclipse everything to private level access by default. So this member is private to engineer. We are inheriting from engineer in civil engineer. And this is going to be already private to engineer, and we can't resurrect this back. So if you eclipse something using private inheritance, you want to be able to resurrect that to a more relaxed access level in downstream classes. This is the message I am trying to convey here. So this is also going to give us a compiler error. And if we try to build our program, we're going to see that. Let's pass this through GCC. We are going to see that the build finished with errors. And if we go back, we are going to get some kind of error that says that do something is private to some class. It is inaccessible within this context. This is the message we get from this particular compiler we are using. But the bottom line is that you shouldn't really try to resurrect something that is already private to an upstream class, and this is what we are doing here. You shouldn't really do that. Let's comment this out and get our code to compile again. So the build is good and we are all fine here. This is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here in this one. In the next one, we're going to explore how constructors work with inheritance. Go ahead and finish up here and meet me there. In this lecture, we're going to zoom in at how derived objects are built. And we're going to zoom in on the constructors that we have been ignoring on purpose so far. So here we have the inheritance hierarchy we will be using. It is what we are familiar with at this point. We have a person class, which is going to be our base class. We have an engineer class, which is now going to be doing public inheritance because we have seen enough of private inheritance. Our engineer class is now going to be nice and say, I am inheriting from person, but I also want my downstream classes to have access to the cool stuff I am getting from person. This is how our engineer class is behaving now. We are also going to have a civil engineer class, which is going to publicly inherit from engineer. But what we want to focus on here is what we get from base classes. So the engineer class is going to have a person part of it, but it is also going to build on top of that and add an engineer level and customize what kind of person it is. So if we inherit from engineer and build our civil engineer class, the first thing to be built by C++ is the person part of this. It is going to build an engineer level of this, and then we are going to add the civil engineer level to add the customizations that the civil engineer class is adding. And C++ is going to do this using constructors. By default, we are going to be using default constructors. If we don't specify a way for the base constructor to be called, C++ is going to call the default constructor to build your base objects. So if we set up something like this and try to run our program, we're going to get output like this. We're going to see that the person default constructor is going to be called first. And notice that we are building a civil engineer object. So the default constructor for the most base class is going to be called. Then we're going to be building an engineer layer on top of the person stuff that we get. Then we're going to build a civil engineer layer on top of the engineer stuff that we have already got. And the compiler is going to do this using the default constructors by default. So we're going to call the default constructor for person first. We're going to call the default constructor for engineer. And then we're going to call the default constructor for civil engineer to complete the construction of our object. The object will be complete at this point, and we will be able to use it later on in our program here. And hopefully this is going to drive the point home that you should really always provide default constructors for your classes. Because the compiler may call these default constructors in unexpected ways, especially if your class is part of an inheritance hierarchy. For example, if somebody tries to build the civil engineer object and you don't have a default constructor for person, the compiler is going to try and call that, and it's not going to find that, and it is going to throw a compiler error, as we are about to see in a minute. Okay, so the message really in this lecture is that the most base part of your class is going to be built. So for example, for our civil engineer class, we're going to build the person part first, then we're going to build the engineer part, and then we're going to build the civil engineer part of that, and then we're going to finish the construction of our object. This is the message here. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is default argument constructor with inheritance. We are going to reuse the code from the last lecture because that's going to give us the classes that we need to play with what we want to do in this lecture, and that's playing with default constructors. Let's put in our starter code, and we're going to open this little guy in Visual Studio Code. Let's do this. So we're going to have our classes. We're going to have the main function, which we can play with. And we are going to look at the person class and make sure we have a default constructor. We are not going to default it this time because we want to have a body. We can put our output statements in. So in this case, we're going to go in the CPP file and put in a default constructor. We're going to say person and person and person here. And this is going to be our constructor. We're going to say stdcout default constructor for person called. Okay, so the person class is done. We have a default constructor that works as we want. And we're going to go to our engineer class and we're going to change it to do public inheritance. I think this is going to be much easier to deal with now. And we're going to remove all these resurrection we were doing here from the last lecture because this is no longer going to be needed. And what we really want is to look at our default constructor, which is really in here already. Let's look at the implementation. All we really need to do is put in stdc out and say default constructor for engineer called. And we're going to hop over to the civil engineer class and see if we have a default constructor, and we do have it. And we're going to go to the CPP file and say stdc out default constructor called for civil engineer. So this is going to basically do what we want, and what we really want to see is how, or the order in which our constructors are going to be called if we build a civil engineer object. As we have seen here, the person part is going to be built first. So this is going to call the constructor from person. And because we are not doing any kind of customization on which constructor is going to be called, the compiler is going to call the default constructor by default. So we're going to build the person part first, and we're going to see the default constructor for person called. After that, we're going to build the engineer part of us, and this is going to call the default constructor for engineer. And after that, we're going to build the civil engineer part of us, and that's going to call the civil engineer default constructor. This is what we want to see if we build a civil engineer object. So we are going to hop over in the main CPP file and actually build the civil engineer object. We're going to say civil engineer, and we're going to say CE1. We can do that. And we're going to see what happens. Let's try and build this program. We're going to build that with GCC. The build is going to be good. We can run it. Let's bring up a PowerShell window we can play with. We want to bring up a PowerShell window we can clear and run Rooster. And you're going to see that default constructor for person called, default constructor for engineer called, default constructor for engineer called. This is what we want to see, and hopefully this proves that the compiler is really going to build our civil engineer object in parts. The compiler is going to see that it is a derived object, and it's going to see all the classes that this is deriving from. So it is going to build the most base part first. After that, it is going to build other layers until it reaches the level where we are at this civil engineer objects. Again, if we put another statement out here, we're going to say hello in here, and we're going to say std_end_out. And I am doing this so that I just have a point where I can put my breakpoint. Some IDEs are not going to like it if you put a breakpoint at an empty line. So that's why I am doing it here. And I am going to try and debug and really show you that we have an engineer and a person part in us. I have shown you this before, but it doesn't really hurt to repeat this because debugging is really cool. It's going to give you more information than you could ever ask for. We're going to hit our breakpoint here, and if we look in our locals, we're going to have our civil engineer object, which is in scope now. And you see that we have an engineer part of us, and the engineer has a person part in it. So what the compiler is really going to do when it is building a civil engineer object, it is going to build the most base part of us. So it is going to build a person part. After that, it is going to build an engineer layer on top of that. And then it is going to build the civil engineer layer. And that's what we see in our output when we get to run our program here. If we go back, we're going to see that we still have our binary. We can still run it. Let's bring up a terminal window we can use to run this. We're going to run Rooster, and we're going to see the order in which our constructors are called. And this is really cool. Now that we have just debugged this program, we can take out this hello line because it's really useless. And this is really what I wanted you to see. Constructors are going to be called in your inheritance hierarchy, starting from the most basic, going down to the most specialized one. So we're going to call the most base constructor, which is person, and we're going to keep going until we reach the most specialized, which is civil engineer here, to build our object. And our object is really going to be built up in layers. This is the message I am trying to convey here. This is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here in this one. In the next one, we're going to see that we can actually actively call a base class constructor from our derived class, and that's going to add much more flexibility in how our objects are built. We are not going to call the default constructor. We're going to be calling our own constructors and have much more control on how our derived objects are set up and built. Go ahead and finish up here and meet me in the next lecture. In this lecture, we're going to see a way we can instruct for custom constructors to be called when our derived objects are being built and set up. In the last lecture, we saw a figure like this. We had an inheritance hierarchy that went from person to engineer and to civil engineer. And we saw that if we set up a civil engineer object, a person part is going to be built first, an engineer part is going to be built on top of that, and the civil engineer part of that is going to be built. And then we're going to have the construction complete for our civil engineer object. But in the last lecture, we saw that this was calling the default constructors. And sometimes you don't want this. You want your objects built in a specific way, for example, through a bunch of parameters that you pass to your constructor. What if you want this kind of setup? This is what we are going to learn about in this lecture. And what we want to end up with is something like this. We will be able to build a person object by passing in a bunch of parameters. We can pass in the full name. We can pass in the age. I think this is the age. We can pass in an address. We can build an engineer object by passing in this kind of information. We can pass in the name, the age, and the address. But we can also pass in the contract count. I think this is the new member variable we had in our engineer class. But we're not going to stop there. We can also build a civil engineer object, and we can pass in the information. Again, a civil engineer is also a person. So we're going to be passing the information that is going to initialize the person part, and that happens to be the name, the age, and the address. But a civil engineer is also an engineer, so we're going to pass information that portrays to the level of an engineer, and that's going to be the contract count. And we're going to pass the information to initialize the civil engineer part of this object, and that's going to be the road strength. And hopefully from this, you can see that we need a way to forward all this information to the constructor where this information is needed. For example, if we are building a civil engineer object, we want to forward the name, the age, and the address to the person part of us. So we need to parse this to our person constructor in a way. We need to pass the 31 here to our engineer constructor because this information is going to be stored at our engineer level. And we need to store the road strengths information into the civil engineer part of us because that's where this member variable is declared. Hopefully you can see the need to call custom constructors which are not default. These custom constructors are going to allow us to forward information when building our objects like we are doing here in the main function. So let's see how we can do this. Some of you might think, if I am building an engineer object, I can just grab the information and pass that to my base class. And that is simple, right? So we can grab all this information. We can grab the full name, the age, and the address, and pass that to our base class using the syntaxes we have here. If we are doing public inheritance, we're going to have access to these guys anyway. So we can say full name equals full name, age equals age, and say address equals address. Except for the address is actually private to the person class, and we can't do something like this. If we try to access the address member variable from the base class and modify it, we're going to get a compiler error that says that the address is actually private to the base person class. We can't do this, so this is not going to work. Okay, some of you might think, what if I try to use an initializer list and do something like this? So I can say m full name and pass in my information. I can say m age and put in my information. I can say m address and put in my information, and then initialize the member variable that actually belongs to the engineer class that we are trying to build an object for here. And hopefully this is going to work, except the compiler is not also going to accept this. The reason is, with initializer lists, you can't initialize a member variable that doesn't belong to the class that you are trying to build an object for. So for example, here we are trying to initialize m full name, m age, and m address, but these member variables don't belong to the engineer class that we are trying to build an object for. So we're going to get a compiler error here. This is not going to work. It is not engineer's job to build or set up these member variables. So this is not going to work. Okay, so how are we supposed to forward information from derived classes to base classes? Not to worry here. We can still use initializer lists, but we are going to use constructors whose job is going to be to initialize these member variables. So if we are building an engineer object and we have information that really belongs to the person part of us, we're going to call the person constructor to actually use this information to build the person part of us. And we're going to be calling the person constructor in our initializer list here. And after we do that, we're going to initialize a member variable that actually belongs to us in our initializer list. And this is going to forward information from derived classes. In this case, the engineer is the derived class, and the information is going to be forwarded to the person constructor, which is our base class. This is how this is going to work. Okay, now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is constructors with inheritance. We are going to grab the code from the last lecture because that's going to be our starting point, and we're going to paste this in our current project. We are going to open this little guy in Visual Studio Code by dragging and dropping here, and this is going to give us our starter code. We're going to have a person class, an engineer class, and a civil engineer class, and this is basically going to set up the hierarchy we have here. And what we want to achieve is to be able to call our own custom constructors when we build our object in layers. Information is going to be coming from a civil engineer object, and we are going to initialize the person part of us with relevant information. We're going to initialize the engineer part of us with relevant information, and we're going to initialize the civil engineer part of us with relevant information. This is what we want to achieve. Okay, for that to work, we need to not call default constructors. We want to call actual constructors that are going to grab the information and forward that in our member variables. For example, in person, we have a constructor which is going to take 3 pieces of information, and it is going to pass this information into our member variables. We need to apply a few changes here. For example, our third parameter is passed as a const string member type. We are going to change this to be std string view because this is going to save us on copies. Let's say string view here. This is going to work. And this is going to forward information in a way we want. We're going to change our third parameter to be std string view. Let's say string view here. We're going to say std string view. This is what we have in our header. We're going to be having the same signature for our function here. And what is wrong? We have m full name, m age, and we have m address here. Let's try to build and see if the error goes away. Sometimes Visual Studio Code is playing games on us. If we get a compiler error, we're going to try and fix that. You see that it is Visual Studio Code playing with us. The code is just fine here. So we have our constructor for person. It is going to forward information using our initializer list here. We're going to look at our engineer class. If we go there, we're going to see that we don't have any constructor which is going to grab information in any meaningful way and put that in our class. So we are going to put in a constructor that looks like the one we have in our person class. So we can just grab this. I like copy and pasting because that's going to save me a few seconds. So I am going to put my constructor here, only it is not going to be called person, it is going to be engineer. And I am going to add a contract count member. And this is going to be an integer here to keep things simpler. And we are going to put an implementation of this constructor in our engineer class. We can go down here and put that in front of other constructors. Let's look at the order we have in our header because I like to be consistent. The default constructor is first, so this constructor is going to be second. And we're going to say that it belongs to the engineer class using a scope resolution operator here. And we are going to put in our initializer list. Now, what we want to do is to call the constructor for person to initialize a person part of us. And then we're going to grab the information for the contract count and we're going to forward that in our own member variable. The way we're going to achieve this, we're going to call the person constructor and we're going to pass in the full name. We're going to pass the age and we're going to pass the address. And then we're going to initialize our own member variable, which is contract count, I think. Let's go to the header and look at that. We're going to see that our member variable is contract count. So we're going to say contract count and we're going to say contract count param. We're going to name this differently because we don't want issues with naming here. So let's name our parameter here param. This is going to not confuse the compiler. And once we have this n, we can just put in the body, which is going to be empty because all the initialization is now done in our initializer list here. So if we do this, we're going to see that the compiler is going to be happy with our thing here. We're going to go down in our civil engineer class and we're going to grab the constructor we have in engineer because we're going to be using this as a starting point. We're going to copy it and go in our civil engineer class. We're going to see that we don't have a custom constructor. We're going to put this in. We're going to name this civil engineer. And we're going to add a specialty member that we want to initialize. So we're going to say std string view because we want to forward string data. We're going to say std string view here. And we're going to say specialty. And we are going to put the implementation of this in our CPP file for civil engineer. We're going to put this below our default constructor. Let's grab this. I lost this somehow, so we're going to copy and we're going to paste down here. We're going to say that this constructor belongs to the civil engineer class. We're going to use our scope resolution operator. And after this, we're going to put our initializer list. In civil engineer, we will call our engineer constructor, and it is going to be taking 4 things. We're going to pass in the full name, we're going to pass in the age, we're going to pass in the address, and we're going to pass in the contract count, which we will get from our constructor from civil engineer, but we will also initialize our specialty member variable. So we're going to say m specialty, and we're going to pass the specialty information here. And this is going to initialize our thing. We're going to put in an empty body, and our information is going to be properly forwarded to our base classes. So if we build the civil engineer object, proper information is going to be forwarded to the engineer part of us, and the proper information is going to be forwarded to the person part of us. Now that we have this in place, we can put in our stdcout statements to let us know which constructor was actually called to build our thing. We're going to say that it was our custom constructor that was called. Let's say that here. We're going to say custom constructor called for civil engineer. We are going to go to our engineer class and also say the same thing. Let's go to the CPP file for that, and we're going to put in our stdcout statement, and we're going to say custom constructor. We can copy this to be consistent with what we had in our constructor, default constructor, I should say. and we're going to say custom constructor called for our engineer class. We're going to go back to person, and we're going to go to the implementation file, and we're going to copy the message from our default constructor, and we're going to put this in and say that the custom constructor was called for person here. So now that we have these guys in, we can go to our main CPP file and include the classes. They are included here. We can try to create a person object just like we saw in the slides, and we're going to try and build this program and see which constructor is called to set up this person object. This shouldn't be rocket science. By now, we know that our custom constructor is going to be called because we are passing 3 parameters which should be forwarded to our member variables through this initialize_list. So let's build with GCC and make sure this is what we expect. We're going to use our compiler here. The build is going to be good as you see here, and if we bring up our PowerShell window and run Rooster, we're going to see that our custom constructor is called. Let's bring up the main CPP file so that we can see our thing. We are passing this information here, and we are printing our person object, and we're going to see that the full name is Jon Snow, the age is 27, and the address is Winterfell called, and all this gibberish we have here. Our constructor is really being called. Okay, so this is working. We can also set up an engineer object and see that the information is being properly propagated to the person part of our engineer object, because engineer is inheriting from person. We are passing the information for the full name, the age, the address, but we are also passing in the contract count, which should be used to initialize the engineer part of us. So we are going to run the test to build with GCC. The build is going to go through successfully, and we can bring up our PowerShell window and run the program again. We're going to see that we're going to print the information for person, custom constructor for person called. But what we really are interested in here is seeing that the custom constructor for person is called for building our engineer object, and then we call the engineer constructor. And again, this falls in line with what we saw in the last lecture. The most base constructor is called first, and then the most specialized constructor is called last. In this case, we are just setting up things in such a way that our custom constructors are called, and we do that from our engineer class by calling the base constructor explicitly using the syntax that we have here in our initialize_list. After we have the base constructor called, we are going to initialize our own member variables, and that's what we see. And in this way, the information for the current class will be initialized properly, and this is what we see here. I think this is a little bit misleading because we still have the information from the person object that we built printed out here. We can comment this out and build again. We're going to pass this through GCC to build our program. The build is going to be good. We can clear and run Rooster, and we're going to see that the custom constructor is called for person to set up the person part of us, and then another layer of engineer is going to be set up in our object to initialize the contract count member variable part of us, and we're going to have the information here. So if we print the full name, we're going to get Daniel Gray, the age is going to be 41, the address is going to be the gibberish we expect here, and the contract count is going to be passed in successfully, and this is really cool. We can also comment this out and set up a civil engineer object. We can do that. Okay, so let's go down and put this in place. We're going to create a civil engineer object. We can close up the left sidebar here to have some more breathing room. We're going to build a civil engineer object. We're going to pass in full name, age, address, contract count, and a speciality, which I think we expect from our civil engineer custom constructor here. That's going to be an STD string. That's what we are passing in here. I should say that's going to be a string view, but we can pass in string data just like this, and the string view is going to take it. So what we're going to see here, we're going to see the person constructor called, the person custom constructor, I should say. We're going to see the engineer custom constructor called, And after that, we're going to see the civil engineer custom constructor called to pass and forward all this information in related parts of our civil engineer object. Let's build and see that this is actually going to even compile. The build is going to be good. We can clear and run Rooster, and we're going to see that this is exactly what we expect. The custom constructor for person is going to be called. After that, the custom constructor for engineer is going to be called, and then the custom constructor for a civil engineer is going to be called. And this really falls in line with what we expect if we are building a civil engineer object. And the civil engineer class happens to be inheriting both from engineer and from person. We're going to have the person part of us built first. And because of this, we're going to see the person constructor called. But in this lecture, the real focus is getting our custom constructor called. So the person custom constructor is going to be called. After that, we're going to call the custom constructor for the engineer part of us. And that's going to set up the engineer specific member variables in our object. After that, we're going to set up another layer of civil engineer in our object. And this is going to initialize the member variable that belong to the civil engineer part of us in our object. So this is really the main goal in this lecture, showing you that you can set up things in such a way that your custom constructors are called when setting up your object in layers as you see here. Okay, now that we have this working, I want you to see that there are some bad ways to do these things, and some people are actually going to try to set things up in that way. The first bad way is to try and initialize our member variables in the body of the class. If you do things like this again, this is going to work because full name and age are going to be inherited publicly from the person class, so the code here is going to work. But we have no way to initialize the address member variable because it is private to the person class. So if we try to access that, we're going to get a compiler error. Let's try this out in code and see the actual compiler error. To try this out, I am going to comment out the good code here, and I am going to copy and put in something that is going to be problematic as we saw in the slides. I am going to paste in my constructor here. I should close my PowerShell window here. And I am going to take out my initializer list because we're not going to be using that here. And we're going to just grab the data and use that to initialize our data in our member variable here. So we're going to grab the full name and say m full name equals full name. We can do that. We're going to say m age equals age. That's the information we get. We're going to say m address. And you see that we don't even have that in autocomplete. So we're going to pass the address. We're going to be stubborn and ignore these squiggly lines. And we're going to say m speciality, and we're going to grab the speciality and pass that in. But you see that line 26 has a bunch of squiggly lines. And the reason is the m address member variable is invisible and not manipulable from our civil engineer class. Again, the reason is that the address member variable is private to the person class. So the civil engineer class has no business initializing this in the body. This is not going to work. So if we try and build this, we're going to pass this through GCC. We are going to see that the build is going to finish with errors. And if we go up, we're going to probably see the error. Person m address is private within this context. And we have no business accessing that in the civil engineer CPP file at line 26. This is what we see here. And this is the offending line. We shouldn't really be doing this. If we comment out this line, this is going to work, but our member variable is going to be left with a junk value. And this is really not good because our address that we worked so hard to set up in our parameter here is just going to be ignored. So this is bad. You shouldn't really be initializing your member variables like this, especially if you have an inheritance hierarchy in your classes. So we're going to comment this out and say that this is really bad. It's going to give you compiler errors. And some of you are going to say, okay, this is not working, but what if we try to use an initializer list directly? Let's see if that actually works. we are going to set up another constructor here, and we are going to set up the data in our initializer list. We're going to say, let's say m full name, and pass in the full name. We can do that. Let's try this out. We're going to say mh, and we're going to pass age. We can do that. And we're going to grab the address, and we're going to pass in address here. And after that, we're going to say m speciality, and we're going to pass in our speciality information. What if we do something like this? But you're going to see that we have squiggly lines here. And the problem with this way of doing things is that the civil engineer class has no business initializing things that belong to the person class in the initializer list. Your initializer list only has the capability to initialize the member variables that belong to the current class. And m full name, mh, and m address don't belong to the civil engineer class. That's why we're going to have a compiler error if we try to set up things in this way. If we're trying to build the program, we're going to get a weird compiler error. We're going to see that the build is going to finish with errors, and it is going to say expected initializer before m full name. And we need a colon here. Sorry for this. So this is not the error we expect, but you see that the moment we do this, we have a bunch of squiggly lines on full name, age, and address. And let's build and see the problem we have. And we're going to build with errors as we see here. If we go up, we are going to see our errors. Civil engineer does not have any field called m full name. We're going to see that civil engineer doesn't have any field called mh, and civil engineer doesn't have any field named m full name or m address here. That's the problem. We have no business initializing these member variables that don't belong to the civil engineer class in the first place. So this is also not going to work. The best bet we have really is to call the base constructor and let that initialize the member variables that belong to our upstream class in the inheritance hierarchy. For example, in our civil engineer constructor here, we need to call the engineer constructor to initialize the engineer part of us. And we're going to be forwarding the information, the full name, the age, the address, and the contract count. The engineer class is in turn going to call its base constructor to forward the information about the full name, the age, and the address. And it is going to initialize its own member variable, m contract count, and the information is going to be passed in correctly. And if we're trying to build our class now, we're going to see that everything is going to work. And I really wanted you to be aware of this, because the moment you understand this, you're going to set up your inheritance hierarchies in a way that is going to make sense, and you're not going to be getting all these weird compiler errors. This is really all we set out to do in this lecture, showing you how you can set up your own custom constructors in your own inheritance hierarchy. And at the moment you do that, you're going to get your classes called in the order that you expect. Things are going to be set up in layers. The base constructors are going to be called in a way that you expect, and your objects are going to be built in a way that you can print them and see the information that you expect set up in your object. If you want, you can also use a debugger to see the information in your thing. So we're going to set up a breakpoint here, and we're going to bring up our debugging tab. We're going to hit the green button to start debugging this program. The binary is going to be set up. Once the build is good, the binary is going to be passed in our debugger, and we are going to hit our breakpoint in a minute. Let's wait for this. So we have hit the breakpoint at line 20. And if we expand our civil engineer object in our locals, we're going to see that we have an engineer part of us. We can expand that and see that we also have a person part of us. If we look at person, we're going to see that the full name is, we can see John Travolta, which is what we are passing here. We can also look at our age. The age is 51, as you see here. And we're going to also have information about our address. If we expand this, we're going to see that the address is this gibberish that we just put in. Tiny dog 42 street, and number 89, we can see this information here, and you can really expand and see all these things that make up our object. For example, we can see the information about the contract count, which is 31, and it is what we are passing when we build this object here. And the speciality happens to be road strength, as we see in our locals here. You can really see all these things. We are going to stop here in this lecture. In the next one, we're going to explore how copy constructors work in our inheritance hierarchy. So go ahead and finish up here and meet me there. In this lecture, we want to explore how copy constructors work with our inheritance hierarchies. And we will still be using the same example we have been using in this chapter. We will have this inheritance hierarchy, and we will still be using the same example we have been using in this chapter. The base class is going to be person. We're going to be inheriting from that publicly to create an engineer class, and we will be inheriting from the engineer class publicly to create the civil engineer class. And with this, we want to be able to copy construct objects. And the code we want to be running is something like this. We have an engineer object. We want to be able to create another object from this engineer object using the syntax here. And from what we already know, this is going to call our copy constructor. The funny thing is, this is going to work by default even if you don't put in your copy constructor. The reason is the compiler is going to insert a copy constructor for you, and things are going to be copied in a way that you expect, because none of our classes is using dynamic memory allocation. So everything is just going to fall in place and it is going to work. But if you happen to need to set up your own copy constructor, we're going to see how you could do that in this lecture. And we're going to start by the base class. We're going to set up a copy constructor for the person class. And this is nothing complicated. We just pass our parameter by reference. This is going to be our source object. And we will be copying the data from our source object to initialize the member variables in the current object that we are copying here. Again, this is a copy constructor, which will be copy constructing from the parameter that we pass by reference. Now, how do we do the constructor for the engineer class, which happens to be inheriting from person? Try to think about that. One way to do things is to set up things like this, and this will be just initializing the engineer layer of our class, but nothing is going to be initializing the person part of us. And this is bad. This is going to call the default constructor to initialize the person part of us, and we will just be left in with junk data that is initializing the person object by default. And all the data we have in our parameter engineer object is just going to be lost for the person part of us. So we don't want to do this. This is bad design. You shouldn't do this. Some of you are going to say, but what if we call the base constructor? We have seen that we could do that, right? But remember, this is a copy constructor. What we have on the left is an object. And it happens to be that if you set up a syntax like this with the copy constructor, the compiler is going to set up a temporary person object and a copy from that object to initialize the person part of us. So this is going to be creating a temporary copy object containing the same data we have in our engineer object. So to some extent, this is going to work. But the problem we still have is that we are using the maddress member variable directly from an engineer object. And from what we already know, this maddress member variable is private to the person class, and we have no business accessing this from an engineer construct. So this is going to give us a compiler error. But know that it is possible to set up a getter in the engineer class that is going to return this address, and you can call that getter here and get this thing to initialize your data. This is going to work, but this is really weird. You shouldn't do this. This is bad design. There is a better way. I am going to show you. But before we look at that way, let's try and summarize the problems we have with this way of doing things. This is not going to be reusing the copy constructor we have worked hard to set up in person. So this is just going to be code duplication. Another thing is that the maddress member variable is private to person. So if we try and use it like this, we're going to get a compiler error. Again, it is possible to set up a getter that could return that, and we could use that getter in this place, but this is bad design. We are really forced to set up a getter that is possibly only used in this place. That's bad design. We don't want to do something like this. Another thing is that this is going to create a temporary copy of person from which we will be copying to initialize the person part of us. We don't want to be making that copy because we hate copies in C++ code. So the best way to do this is to set up your copy constructor in this way. We are going to say person and directly pass in our engineer object. The compiler is smart enough to see that we are passing an engineer object to initialize a person object. And what the compiler is going to do is really smart. Suppose our engineer object is made up of two layers. The inner layer is going to be containing the information about the person part of us, and the outer layer is going to be containing the engineer part of us. Okay, so this is the setup we have. So the compiler is going to see that we are passing in an engineer object to initialize a person object, and what it is going to do is really smart. It is going to strip off all this engineer part. If I can describe it like this, we're going to strip off all this engineer part that we have in our engineer object, and we will be just left with the person part that we pass then to initialize our person object. And this is really smart, and it is going to work. So again, the syntax is what you see here. We say person, we pass in our source object, and then we can initialize the member variable that belong to the engineer part of us. We will be initializing contract count, and this is going to work. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is copy constructors with inheritance. We will be reusing the code from the last lecture, so we're going to grab everything from that except for the binary, and we're going to copy that and put that in our current project. Let's do this. And we are going to open this bad boy in Visual Studio Code by dragging and dropping here. And we will have our starting point. We will have our person class, the engineer class, and the civil engineer class. And we will just be doing public inheritance to make things easier here. So engineer is going to publicly inherit from person, and civil engineer is going to publicly inherit from engineer. And this is everything we had from the last lecture, nothing special. But what we want is to set up copy constructors in such a way that we will be able to build objects from others. For example, if we leave in our engineer object, I think this is what we used in the slides, we're going to have our engineer1 object. We want to be able to create another engineer, let's say engineer2, and build that from engineer1. The thing that might be puzzling to some of you is that this is going to work out of the box, even if we didn't really put in a copy constructor. But the thing is, the compiler is going to insert a copy constructor for you, but that constructor is going to be member-wise copy. So it is basically going to be copying things member-wise. It is going to take the contract count from engineer1 and copy that into engineer2. And we are basically going to have the same data from engineer1 in engineer2. Let's try and print engineer2. Can do that. We're going to say eng2, and we're going to put this out. And we are going to run the task to build with GCC. That's what we want here. And you're going to see that it is going to work out of the box. If we bring up a PowerShell window and run Rooster, we're going to see that we have the data in here. We have engineer full name, Daniel Gray. That's the data we have in engineer1. But notice that we are printing engineer2 here. The age is going to be 41, and the address is going to be exactly what we had in engineer1. And you're going to see that the constructors are going to be called to set up engineer2, and the custom constructor for person is going to be called, the custom constructor for engineer is going to be called, and this is exactly what we expect here. But what if we want to set up our own copy constructor? And the need to do that might arise if we happen to be doing some dynamic memory allocation in our classes. Suppose maybe person class has some dynamic memory allocation, it has some pointer member variable, and in the person custom constructor, we are doing some dynamic memory allocation to initialize that pointer. We may be doing the same thing at the engineer level or the civil engineer level, and that will force you to set up your own copy constructor, and we're going to see how you could do that in your classes. We are going to start with the person class. We're going to go on top and set up a copy constructor in front of our destructor here. We're going to say person, and we're going to say const person reference source. This is the syntax you use to set up your copy constructor. You already know this from a previous chapter, and we're going to put in the implementation for this. We're going to go in the CPP file before the destructor, or we should go after our custom constructor. It doesn't really matter where you put this. And we're going to put in our scope resolution operator. Let's do person here. And we will just be copying data from the source person. So we're going to put in our initializer list, and we're going to say m full name. We're going to grab the name from the source person. We're going to say source m full name. We're going to initialize the age. We're going to say m age, and we're going to grab the age from the source person. So m age here. And we can go to the next line so that we see the entire thing here and say m address, and we're going to say source and say m address. This is going to set up our constructor, and down below we can put in our body. This is going to work, but this is everything we have seen so far. This is nothing new. The syntax to set up your copy constructor, you just pass it by const reference. If you don't pass by reference here, you're going to get an endless chain of copy constructor calls. If this is confusing to you, please go back to the chapter on classes. You're going to see everything about this. And this is really all we need to do here to have a copy constructor for person. Now, let's do things at the engineer level. We're going to go to our engineer class, and we need to set up a copy constructor. The syntax is going to be the same. We're going to say engineer, and we will be constructing from a const engineer object we pass as a parameter here. So we're going to say const engineer by reference and say source. And the problem is going to be how we implement this thing. We're going to copy this and go in our engineer CPP file. We're going to put our copy constructor after our custom constructor. And we're going to put in our scope resolution operator. We're going to say engineer, and we're going to put in our body. Let's go below and put that in. If we do things like this, this is just going to initialize our engineer with junk data. We don't want that. But some of you might say, I don't know how to call my base constructor, but at least I can initialize my contract count. Okay, let's go back and see if we have this member variable here. Yes, it is called contract count. We can say contract count here, and we are going to initialize this with source contract count. This is going to work, but this is going to call the default constructor of person to initialize the person part of us. And let's go back in our main CPP file and see what we are using to try things out. We are building an engineer object from another. Let's try this out and see if our copy constructor is called here. So we're going to say custom copy constructor called for engineer. We're going to put in the message, and we're going to say custom copy constructor, and we're going to build our code. Let's build. We're going to pass this through GCC to see what happens. The build is going to be good, and let's see what happens. We're going to clear and run Rooster. We are going to see that the constructors are going to be called to set up person one, but we'll see that the copy constructor for engineer is called. And what I want to do to really make this super clear is put a separator between these two guys. To really know what is happening here, I am going to put in a bunch of dashes just like this. I am going to put in my new line character, and I am going to build again. The build is going to be good. As you see here, we can clear and run Rooster. Now we are going to see that the default constructor for person was called to set up the person part of us in our engineer copy constructor. And the reason is we are not doing anything to call the custom copy constructor from person. And let's go back in person and make sure we are printing proper information to really see this. When we get to do this right, we are not putting in any method here. So we should do that. We are going to say custom constructor or custom copy constructor called for person, but this is not called. You see that we are calling the default constructor, and this is going to initialize our person part with junk data. If we print engineer2 here, you're going to see that the full name is none, the age is 0, and the address is none. So we are basically getting the default data we have in our person object. Let's go back and really show you that. The default full name is going to be none, the default address is going to be none, the age is going to be 0 by default. And this is what we get because in our copy constructor, we're not doing anything to get our custom constructor in person to be called. Okay, so this is not going to work. This is bad. We don't want to do something like this. But let's comment this out and show you another way we might try to do things. And we are going to copy our copy constructor. Let's go down and do this. We're going to put in another copy of this, but we don't want to just initialize our contract count member variable. Instead, we want to do something else. We're going to put a comma here, and we're going to say person. Some of you might be thinking, what if we call the base constructor directly? We can do something like this. We can say person, and we can say source m full name. We can do that. We can say source m age, and some of you are going to say source m address. Let's do that. Source m address, and we're going to build a person object and use that to initialize the person part of us. We are basically going to be calling the other person constructor that we have, which takes 3 parameters. This constructor here, this is what we are trying to call in our copy constructor. But as we saw in the slides, this is going to have a bunch of problems. This is going to be creating a temporary person object that we are going to be copying from to set up the person part of us. But another problem we have, which is actually going to cause a compiler error, is that we don't have access to the m address member variable from an engineer constructor. And this is going to give us a compiler error. Let's actually try and compile this program to really show you this. We are learning. We should really see as many compiler errors as we can. So the build is finished with errors, and if we go up, we're going to see that our error is the m address member variable is private to the person class, and we have no business accessing that in the engineer CPP file at line 27 in our constructor here. And this is going to be our offending line. We can't do this. One could go in our person class and set up a public getter method, which is going to be inherited by engineer. And we could call that to return the address. Let's actually do that to show you that you can do that. So we are going to go in and put in a public method, which is going to return the address. We actually have that here. So we can call that. We can say source get address. This is going to work. This is going to set up our thing. Let's try to build, because I think Visual Studio Code is messing with us here. Okay, you see the build is good. It is Visual Studio Code, which wasn't understanding our code here. And if we run our program, we're going to see that things are going to work exactly as we expect. Let's actually run the program here. We're going to clear and run Rooster. We're going to see that now the information is being forwarded properly, but we are setting up a temporary person copy, which we are copying from to then forward the data to the person part of us. This is not good design. And what we really want is a setup that is going to allow us to call the copy constructor that we worked hard to set up in our base class here. Let's go back to person and see that. If we go up, we're going to see that we have a copy constructor we really worked hard to set up. We want to reuse this in our engineer class. And that's what we're going to see here. So this is working, but it is not optimal. And we should really try to reuse our code as much as we can. So what we're going to do is set up a mechanism that is going to reuse the copy constructor we have in person. And all we need to do to get that to work, we can say person and then call the copy constructor of person by directly passing in our source object. Notice that we don't need to set up a temporary person object. We will directly be copying from our engineer object, but this is going to do the slicing we saw in the slides. Again, if we have 2 layers on our object, the inner layer is going to be the person part of us, and the outer green layer is going to be the engineer part of us. what the compiler is going to do, the compiler is going to see that we are actually passing in an engineer object to initialize the person part of us here. And it is going to see that we just need the red part, we don't need the green part here. The compiler is really smart, so it is going to slice off the outer engineer layer and only leave in the green person part. And it is going to use that to initialize the person part of our engineer object. And this will be reusing the copy constructor we have in our person object. And this is really cool. This is the optimal way to set up your copy constructors if you have an inheritance hierarchy. So let's try and build the code again. We're going to pass this through GCC to see if this actually works. The build is going to be good. We can clear and run Rooster. We're going to see that the copy constructor is going to be called for person to set up the person part of us. And then the custom copy constructor for engineer is going to be called to set up the engineer part of us. And if we look at the information we have in the main function, we're going to see that it is the same data, Daniel Gray for the full name, age is 41, address is this gibberish here, and the contract count is 12. It is exactly what we passed here, and our copy constructor is working. Now that we have this working, we can safely reuse the same ideas in our civil engineer copy constructor. We can head over in our civil engineer and set up a copy constructor. So let's do that. We can close the left sidebar here so that we see the entire thing. We are going to say civil engineer, and we want to set up a copy constructor. So we're going to say const civil engineer here, and we will be passing this by reference. We're going to say source, and we're going to put the implementation of this in our CPP file. We can hop over there and go below our custom constructor. We can put in our constructor here. We're going to say civil engineer and put in our scope resolution operator. And we're going to go down and put in the body. And in our initializer list, we're going to call the copy constructor from engineer, because remember, civil engineer is inheriting from the engineer class. So we are going to call the engineer copy constructor. We're going to pass in source. And again, this is going to slice off the civil engineer part and only use the engineer part of us to construct an engineer object from this sliced off engineer object we get from our copy constructor here. And this is really cool. After that, we will initialize our contract count member variable. Oh, it is M speciality if I remember correctly. And we're going to grab source M speciality, and we will use that to initialize the civil engineer part of us here. Let's go in and say that the custom copy constructor is being called here. And we're going to say custom copy constructor called for a civil engineer. What did we do here? We said engineer. Let's do engineer. This is what we want. And we're going to say engineer here properly. Sorry for this, but this is no big deal. And now that we have this in place, we can actually build civil engineer objects and copy construct them. We can comment out the engineer stuff we have, and we can just put this in a block comment. And we're going to copy construct civil engineers. How cool is that? We're going to set up a civil engineer. Let's do that. And this is going to be a civil engineer. And we're going to say Daniel Gray. We're going to put in all the data, and we're going to specify the speciality to be road strength. This is something I just made up. I don't even know if this kind of speciality exists. And we will set up another civil engineer object called eng2, which we are going to be copy constructing from. And we will see what happens when we copy construct this thing here. We should call our copy constructor in civil engineer, and things should propagate up all the way to the person part of us, and we're going to see what happens. Let's build this code. We're going to pass this through GCC as we always do. The build is going to be good, so this is good news. We're going to clear and run Rooster. And we're going to see that the custom copy constructor is called for person. The custom copy constructor is going to be called for engineer. And the custom copy constructor is going to be called full civil engineer. And you see that things are really propagating all the way to the person part. And we are calling and reusing our copy constructors. And this is really cool. If you go down, you're going to see that the information is printed out correctly. The full name is Daniel Gray, which we have in Engineer 1. The age is 41. The address is all this gibberish. The contract count is 12. And the specialty is road strength. And we are properly reusing our copy constructors in our inheritance hierarchy. This is really all I had to share in this lecture. Again, the syntax you should be using to set up your copy constructors is what we see here. This is going to be reusing the code we have in our upper classes in our hierarchy. We will be avoiding the temporary copies we saw when we called the other constructor directly. And this is much cleaner. It is reusing code we have in other classes. We are going to stop here in this lecture. In the next one, we're going to see that it is actually possible to inherit base constructors. Go ahead and finish up here and meet me there. In this lecture, we're going to explore the fact that we can inherit base constructors and use them in our derived classes. We will be reusing the same hierarchy we have been using, so we will have the person class, and we will be inheriting from this person to create an engineer class, and that's what we're going to be using to learn about this concept here. So the person class is what we know from the previous lectures. We have a bunch of member variables here. We have the full name, the age, and the address. And we have a bunch of constructors now. We have a default constructor, a custom constructor, and a copy constructor that we set up tirelessly in the last lecture. Now, what do we mean when we say that we can inherit a constructor? Well, base constructors are not inherited by default. And what we mean by that is that by default, it is really not possible to get derived classes to use base constructors to set up things. But it is possible to tell the compiler to use the base constructor to set up our own objects. For example, we can put our statement here saying using person, : person. This is going to tell the compiler when building engineer objects, don't use your own constructor, set up a base-like constructor, which is going to only initialize the base member variables. And the compiler is going to see this statement, and it is going to generate a constructor for you that looks something like this. So it is going to be engineer, it is going to be taking in the full name, the age, and the address, and it is going to be forwarding the work to initialize your object to the person class, and this is all this constructor is going to do. Hopefully you can see that this is called inheriting a base constructor, because all this constructor is really doing is initializing the base member variables. It's not initializing any member variable that belongs to the engineer class. So the engineer part of us is going to be basically empty, containing junk data that we get by just calling the default constructor, and we will only be initializing the data belonging to the person part of us. This is really what I want you to see. Again, the syntax is what we see here. This is going to tell the compiler to generate a constructor that is only going to initialize the base member variables, but this constructor will be callable and usable from the engineer class. Okay, so this is really what we mean by inheriting constructors. One thing you should know is that the constructor is going to be inherited with whatever access specifier it had in the base class. So if our constructor was in the public scope, it's going to be inherited with public access. So we will be able to use it from the outside and build engineer objects. If it was in a protected scope, we won't be able to use it from the outside. If it was private, we won't even be able to use it from a derived class. You should really know that. So it is going to be inherited with whatever access specifier we had in our base class. Now that we know this, let's see some things you should really be careful about. The first is that copy constructors are not inheritable. If you try to do that, you're going to get a compiler error, but you won't usually notice this because the compiler is going to insert copy constructors for you anyway. This is going to become a problem if you are doing some dynamic memory allocation and you're going to get pointers copied. This is really bad. If you don't know about this, please go back to the chapter on classes and you're going to see all the story about shallow copying and deep copying. We talked about these things. Another thing you should know is that inherited constructors are really base constructors, and what we mean by this is that they will only be initializing the base member variables. Because they are base constructors, they have no knowledge of derived member variables. That's why they only initialize base member variables. Again, as we said, the constructors are inherited with whatever access specifier they had in the base class, and it is possible to set up your own constructors on top of the inherited constructors, and you can use these things. Another thing I should really tell you is that inheriting constructors is going to make your code really confusing. It is a technical possibility, but I strongly advise against using this in your code because it is just going to confuse people. People are going to see, for example, an engineer constructor, and they are going to think that that constructor is going to even initializing the engineer member variables. But it's not going to do that because it is a base constructor. It's only going to be initializing the base member variables, and that may lead to some confusion or even really bad problems in your code. So don't use this. It is just going to make things confusing. But I wanted you to be aware of this. And if you see this kind of setup in classes out there, you will know what they mean. This is just going to inherit a base constructor and use it to build objects. Now that we know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is inheriting base constructors. We are going to steal code from the last lecture, and we will be using the main CPP file, the person class, and the engineer class. This is just going to be enough for our purposes here. We're going to go back in our current project, and we're going to put this in. And we will open this in Visual Studio Code by dragging and dropping here. This is going to give us our thing. And let's go to person and see that we have our constructors in. We have a default constructor, we have a custom constructor, and we have a copy constructor. One thing you should know is that copy constructors are not inherited. So you will need to set up your copy constructors explicitly if you want to use them. Note that they won't be coming from the upstream class. You should know that. Okay, so this is the message here. Now, let's look at our engineer class. The engineer class is publicly inheriting from person, and it has a bunch of its own constructors. But what we want to do is to take out all these constructors, and we're going to take them out. I think we can, we're going to take them out. Let's do that. And we're going to go in our CPP file and also take out all these constructors here. We're going to comment them out. I think we can take out all these bad code we got from previous lectures, and we're going to just comment out our constructors. We're going to close them all with a block comment. And what we are going to do in our class is say using person. We're going to say using person. This is going to inherit the constructors from person. And now that we have this in place, the compiler is really going to generate a base-like constructor in our engineer class. In other words, we're going to have a default engineer constructor, which is just going to not initialize anything. We are going to have a custom constructor, which is going to take 3 parameters, but it is going to be an engineer constructor. And let's prove this. We're going to go in our main CPP file, and we're going to take out everything we have here. And we don't have a civil engineer file, so we shouldn't really include that. And we are going to create an engineer object. We can say enc1. Using the default constructor, we can try and print that out. And you're going to see that this code seems to work in Visual Studio Code. We can try and build this. We're going to pass this through GCC, and we are going to set up a PowerShell window we can use to run and see things. And we're going to see that the default constructor for person was called to initialize this guy. And the data is really junk data we have in person. So what the compiler is really doing behind the scenes is to generate a base-like constructor at the engineer level, and it is going to call the base constructor to initialize the person part of us. So the data is just going to be junk data we have in person, and you're going to see that the contract count is going to be 0. This is just a default constructor, which is just going to grab whatever default data we have in our object. You see the contract count is 0. If we go back in person, we're going to see that the full name is none, which is what we see here. The age is 0 and the address is none. This is a default constructor. But we can even explicitly pass in the data, and that's going to also work. So we can pass in the full name to be Daniel Gray. We can pass in the age to be 23, for example, and we can pass in a junk address, let's say something like this. And you see that this is going to work even if we don't have any engineer constructor. That takes 3 parameters. Let's go back and you're going to see that all our constructors are commented out, but this is working because we told the compiler to generate a base-like constructor for our engineer. So it is going to also have an engineer constructor that looks like this constructor here, which takes in 3 parameters. And this is really cool, and this is really crucial to understand. So again, we are going to set up a constructor for engineer. So it is going to be an engineer constructor, but it is going to be taking 3 parameters, just like the person constructor here. And this is the message I really want to convey here. So if we run this code, you're going to see that it is going to work. It is going to call our base-like constructor for engineer, and we're going to have the data forwarded in, but you're going to see that the contract count is not going to be taken into account. So it is going to still contain some default data. If we try and pass that in, we're going to see that we're going to get a compiler error because now we have no such constructor that takes 4 parameters. The only one we have is one that is generated because of this statement here. And this is going to be a base-like constructor, which is just going to take 3 parameters, just like this constructor here. And another thing I don't think I made clear enough is that this is going to bring in all the constructors you have. Notice that we just put in this statement, but it is going to grab all these constructors we have, except for the copy constructors, which are not inherited in C++. So you should really know this. If we build this code, we're going to get a compiler error because the compiler wants to know what to do with the 45 parameter that we have here. But let's build and really show you this. You need to see this compiler error with your own eyes. Let's go in. So the build is finished with errors, and we have an error saying no matching function called to this constructor, which takes 4 parameters. If we take this out, we're going to see that this is going to work. This is going to use the compiler generated constructor as a result of this statement we have in our code. Now, if we build, we're going to see that this is going to work. Okay, the build is good. We can clear and run Rooster. We're going to see that we have the full name to be Daniel Gray. We have the age to be 23. We have our address, which is really some junk data, and the contract count has no data in. It is just the default data we have in our member variable here. We have no way to initialize this from a base-like constructor. But not everything is really bad news. If you don't want to be limited by the constructors that are generated by your compiler as a result of inheriting, you can set up your own constructors. For example, we can uncomment our engineer constructor here and bring it out of our comment. We can do something like this. We can go in the implementation file and also bring this out of our comment section. And now we will be able to use this constructor, which is going to take the 4th parameter here and do something with it. Now, if we go back in main, the code with 3 parameters is going to work. It is going to use the compiler generated constructor. But if we pass the contract count to be 4, this is also going to work because it is going to be using our own constructor here. If we build the code, we're going to see that it is going to work just fine. Let's use GCC to show this. You're going to see that the build is good. We can clear and run Rooster. Now our contract count is taken into account, and this is really cool. This is really all I wanted you to see in this lecture, that you can let the compiler generate a base-like constructor using the syntax we have in our header here. This using statement can really show up anywhere, but it is going to inherit the constructor with whatever access specifier the constructor had in the base class. And you should really keep these points in mind, especially the last one, that inheriting constructors is going to make your code confusing. People are going to notice that they can call constructors that are really not going to be initializing derived member variables, and this may cause serious problems in your code. We are going to stop here in this lecture. In the next one, we're going to explore how inheritance works with destructors. So far, we have been ignoring destructors. We are going to focus on them in the next lecture. So go ahead and finish up here and meet me there. In this lecture, we're going to focus on how destructors work with inheritance. And suppose we have an inheritance hierarchy like we have been using all along in this chapter. So our base class is person. We have the engineer class, which is publicly inheriting from person. And we have a civil engineer class, which is inheriting from engineer publicly. So when we create a civil engineer object, we have seen that the base part is built first. So we are going to build the person part of us. We are going to build the engineer part of us on top of that. And we are going to build the civil engineer part of us on top of that. So the constructors are going to be called in this order. We will call the person constructor first, engineer constructor after that, and then a civil engineer constructor after that to set up our civil engineer object. The thing I want you to see in this lecture is that the structures are called in the reverse order to that. So the most specialized destructor is going to be called first. Then we're going to destroy the engineer part of us, and the person part of us is going to be destroyed last. So we are going to construct things in this order from the base part to the most specialized one, and then we are going to destroy things in this order. So the structures are going to be called in the reverse order than the constructors. That's the message I want to convey here. And we're going to set up a simple example to play with this. We're going to create a civil engineer object, and we're going to see the order in which these things are called. And let's head over to Visual Studio Code and actually do this. Here we are in our working folder. The current project is inheritance and destructors. We are going to be reusing the code from a previous lecture. I don't think the last lecture is a good example because we don't have a civil engineer class. So we are going to go to the lecture before that and use the code from our lecture on the copy constructors with inheritance. That's going to give us all the classes. We have person, engineer, and civil engineer, and we need that in this lecture here. So let's grab all these things. We're going to copy them and put them in our current object, which is inheritance and destructors. And we are going to open this in Visual Studio Code, and it is going to be our starting point here. So we have person, engineer, and civil engineer. Let's see what we are doing in the main CPP file. We can take out all the junk here, or we can leave in the civil engineer object we are creating here. And we're going to see how the constructors and destructors are called. We're going to go to person and make sure we have a constructor and we have a bunch of constructors and let's go to the CPP file and see that we have messages in our constructors. This is really what we expect, but we want to also put a message in the destructor. Let's say stdc out and say destructor for person called. This is going to do. We're going to go in our engineer class. We're going to see that we have a bunch of constructors. We have a destructor here. We're going to hop over in the CPP file and make sure we take out the bad code here because we don't really need that. We only need good code. And we make sure that we have output statements in our constructors to know when they are called. Looks like we are good. We're going to put an stdc out statement in our destructor for engineer called. This is going to do. And we are going to hop over in our civil engineer class. We're going to have a bunch of constructors. We're going to have a civil engineer destructor. We can go in the CPP file and make sure that we have output statements in our civil engineer constructors. Looks like we are good here. We can take out all the bad code we don't need. And we are going to put a message in our destructor here. So let's do that. The destructor called for civil engineer. I think this is going to be good enough. Let's go back and make sure we have the same messages here for engineer. and we have a destructor for person called message. And we're going to try and run the code and see how constructors and destructors are called. This is the order we want to make sure we understand. If you want, you can even use a debugger to follow things, but I am not going to do that here. I am just going to build and show you the output statements. Hopefully, that's going to be proof enough that things happen in the order that I just described in the slides. The build is good, we can clear, we can bring up a PowerShell window and then clear, and we're going to run Rooster. We're going to see that the constructor is going to be called for person, for civil engineer, and you're going to see that things are going to happen from the most base constructor to the most specialized constructor. So we are going to call person, engineer, and civil engineer, but you're going to see that destructors are going to be called in the reverse order. The most specialized destructor is going to be called first. Then we're going to call the destructor for engineer. Then we're going to call the destructor for the base class. So things are going to be happening in reverse order. We will build things starting from the base and then finish by the most specialized class, which is doing inheritance. And then we're going to call the destructor for the most specialized class first. And then the destructor for the most base class is going to be called last. You should really make sure you understand this, because sometimes your things are going to be depending on this order and you need to understand this. And this is really the main message here, that destructors are really called in the reverse order than the constructors. We are going to stop here in this lecture. In the next one, we're going to see that we can actually reuse names in our inheritance hierarchy. And we're going to see how that works out in the next lecture. So go ahead and finish up here and meet me there. In this lecture, we're going to see that we can reuse names in our inheritance hierarchy. And what we mean by that is that we can have a parent class, for example, and have a child class inheriting from the parent class, and have exactly the same names for the member variables and types, or the same signatures for functions. For example, in the parent class, you see that we have a member function called print_var. It is going to be printing some information. We can have a function named exactly the same in the child class, and C++ is going to allow this. We can also do the same things for member variables. For example, we have mvar, which is of type int. We have exactly the same thing in our child class, and C++ is going to allow this. Now, the problem is, if you create an object of child, which method will be called if you call print_var? Now, what C++ does is it is going to override or hide things you have in the base class if you happen to set up exactly the same thing in a derived class. So for example, the members in our child class are going to hide the members we had in the base class. And if we call these methods on a child object, we are going to get the versions in the child class called. If we call these methods on a parent object, we are going to get the parent version called, and we're going to see the data in the parent class printed out. This is the message here. It is possible to use the same names in both parent and child classes, and if you do that, things in child classes are going to hide or override what we had in the parent class. This is the message I want to convey here. And here is a simple example to drive home how you can use these things. For example, we can create a child object using this syntax here. And if we call a method on the child object, this is going to call the method in child. But it is possible to force the compiler to call the version in the base class. And you're going to see this syntax used somewhere in your code out there. So the syntax is to say the object name, you put a dot, you say the name for the parent class, and then you call the method using the scope resolution operator here. And this is going to call the method in the parent. Okay, now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is reused symbols and inheritance. We are going to just grab the template files because we are going to be building things from scratch here. And we're going to put in our files, no big deal here. And we can open this in Visual Studio Code. This is going to give us a bare minimum main CPP file. We can clean it up a little bit. And we're going to set up our parent class. Let's do that pretty fast. We're going to say parent and set up the header. And we're going to set up the implementation CPP file. We are going to set up the header file, and this is going to do everything we want. We have a constructor which is really defaulted here. So let's say default, and we can default the destructor. Can we default it? Let's do this and see what happens. And we don't really need to do anything in the CPP file. We can leave it empty. This is not going to hurt anything. And with this, we can create parent objects. Let's do that. We're going to hop over to the main CPP file and include parent and make sure that we can use that. And we're going to create a parent object. Let's do that. We're going to say parent p1 and say p1 print values. We can do that. And we can build and run this program. I think it is going to work just fine. Okay, the build is good. We can clear, or we can set up a PowerShell window and clear and run rooster. This is going to say the value in parent is 100, which is what we have by default here. We have a simple member variable, which is of int type. It is protected because we want it to be inherited. And we have a bunch of constructors here. We have a constructor which is going to take a value, but we're not going to use that here. The default is just fine. You can use that if you want. And we have a member function which is going to print the value in parent. Now that this is working, we can set up a child class which is going to be inheriting from the parent class here. So let's do that. We're going to set up the child header file, child.h, and we're going to set up a CPP file for that, .cpp. So we are going to put the data in the header file. Again, it is nothing complicated. It is just a simple class which is going to be inheriting from parent. And we are going to have our own member variable, which is going to eclipse what we had in the parent. So the names here must be the same, mmember var. If we go in parent, it is mmember var. And what we have in child is going to eclipse what we had in the parent class. In other words, if we print the member variable in child, we're going to see 1000 printed out here. We won't see 100 that we have in the parent printed out. Hopefully this is going to drive the point home that if you have members named exactly the same, what you have in your derived classes is going to eclipse or hide what we had in the parent class. This is the message here. But even if this is the case, C++ allows us to specify that we want to grab the data in parent from a child object. For example, in our show values method, we can print the value in child directly using mmember var, but we can also specify that we want the value in the parent class, because even if this is a child object, it has a parent part of it. So we can access the data in parent and print that if the data happens to be accessible from our derived class. And that's why we set up our member variable to be protected, for it to be accessible in our derived classes. This is going to allow us to print something like this, and this is going to really work. Now that we have this in place, we can go in the main CPP file and only include the child. We can do that. And we're going to create a child object. Or we can just take out everything here and just put in the code we can use to play with these things. We can create a child object, and on this child we can print var. We're going to see that the data is going to be printed out, but we can also use this syntax to print the data in the parent part of us, and we're going to see that the data is printed out. We can also show the values and make sure we see this from a member function of the child class. This is going to call this member, and we're going to get the value in child, and we're going to get the value in parent printed out on the console. Now that we have this, we can actually try and build this. We're going to use GCC to do that. We're going to see that we're going to finish building with errors. What is the problem here? We have an undefined reference to child destructor. We didn't put in a definition for the child destructor, so let's go there and default it. We can do that. We're going to say equals default, and the compiler is going to generate one for us. And now if we build, we're going to build with GCC again. The build is going to be good. You can clear and run Rooster, and we're going to see that the value in child is 33 because we passed that in explicitly. And this is going to call the constructor we have in child. That happens to be this guy here. And you see that we are really keeping things simple. We are not calling the base constructor here. The compiler is just going to call the default constructor we have in parent here. And this is going to just work. The main message here is that you can set up member variables and member functions named exactly the same way in the parent class and in child classes. And what you have in your derived classes is going to hide what we have in our parent classes. So if we call a method on a child object, for example, like we are doing here, this is going to call the method in child, but we still have the ability to call data in the parent part of us. And this is what we do here. I would like to welcome you in this new chapter where we're going to be learning about polymorphism. And polymorphism is the setup we can do in our C++ programs to use a base pointer and manage derived objects. Suppose we have an inheritance hierarchy like we have here. We have shape as our base class, and we can inherit from oval and create a circle class. Imagine that we can create all kinds of crazy shapes that inherit from shape in our C++ program. For example, we have a rectangle class, we have a triangle class, we have all kinds of crazy shapes. Now, if we have this inheritance hierarchy, here is something we might want to do. We might want to set up a base pointer that is managing a derived object and set up code like this. For example, we say shape pointer, and I set up a pointer variable here and use this pointer to manage a circle object that we dynamically allocate for on this line here. We can also do a shape pointer that is managing a rectangle. We can set up a shape pointer that is managing an oval object. We can really set up a base pointer that is managing any kind of object we support in our inheritance hierarchy. Now, some of you are going to ask a few questions. One of them is going to be, is this even legal C++ syntax? And the answer is yes, because if circle is inheriting somehow from shape, a circle is really a shape. And if rectangle is inheriting from shape, it is a shape. And if we try to assign a circle to a shape, we're going to see that that's going to work. So this is valid C++ syntax. And we can do the same thing using references as we see here. We can set up a reference that is going to be managing a circle object that we have through circle 1. We can set up a reference to manage a rectangle that we have in shape 2. We can set up a reference to manage an oval object. We can really do all these things. Now, some of you are asking, why would we want to do something like this? Now, try and think about your inheritance hierarchy here and try to think about what if you want to draw this kind of shape, for example. If you didn't use polymorphism, you would need to set up all kinds of crazy methods to draw each kind of object. And we have no way around this because these are different types. If you have a method that takes an oval and you pass in a circle, that's going to give you a compiler error. But with polymorphism, we can set up a single method which takes a shape pointer or a shape reference, and we can pass in all kinds of crazy objects whose class derive from shape. So for example, we can pass in the address of the circle, and this function is going to draw a circle. We can pass in the address of a rectangle. This is going to draw a rectangle. We can pass in the address of an oval, and this is going to draw an oval. Hopefully you can see how this is useful. We can even do this using references. So if we pass in a rectangle, this is going to draw a rectangle. If we pass in a circle, this is going to draw a circle. You get the idea. This is one of the benefits of using polymorphism. Again, polymorphism is about using base class pointers or references to manage derived objects in our inheritance hierarchies. Another benefit of polymorphism is to allow us to be able to store different kinds of objects in a single collection. Remember, an array can't store objects of different types. If you set up an int array and try to store in a string or a double, you're going to get a compiler error because that's not allowed. So if you have an array that is going to store circles, you can't put in an oval, you can't put in a rectangle, you can't put in a star. You can't really do that because an array by design is going to store objects of the same type. But we can avoid this limitation using polymorphism. Again, we can set up an array that is going to store base class pointers, and we can store in all kinds of crazy objects whose class derive from this base class here. So here we can store in a circle object, we can store in an oval, we can store in any kind of object that is part of our inheritance hierarchy with the base class as shape, and this is going to work, and this is going to be using polymorphism. For example, if you loop through this collection calling the draw method, for the first element, this is going to call the draw method on the circle. For the second element, we're going to call the draw method on an oval, and this is going to be really cool. This is something we can achieve with polymorphism. And I want to back up a little bit and talk about what is really meant by polymorphism. Polymorphism really means multiple forms. And in my opinion, what this means is that the base class pointer or base class reference can take multiple forms. At one point, it might be managing a circle. At one point, it might be managing a rectangle. At one point, it might be managing an oval object. So it is a base pointer, but it can take multiple forms because it can be managing multiple kinds of objects whose class are part of our inheritance hierarchy. This is what we mean by polymorphism. So again, the idea is that we can use a base class pointer or reference to manage all kinds of crazy objects in our program. And this is going to have many benefits as we are about to experience in this chapter here. I am really excited to be explaining this to you. This is one of the most powerful features in C++. We are going to start in the next lecture and show you that you don't get polymorphism by default in C++, and what you get is static binding. Go ahead and finish up here and meet me there. To manage derived objects in our C++ program, hopefully this is going to give you a clear idea on why we might need to do this. So let's look at our classes that we're going to be using here. We're going to set up a shape class which is going to be representing our shapes. This is going to be our base class. That's the basic use for this here. It has a simple member variable which is going to store the description for our shape. It is also going to have our draw method, which is really not going to draw anything. It is just going to say the description for our shape here. Once we have this shape, we can create other shapes from it. For example, we can create a novel class, which is going to be representing a shape like this. It is going to have two member variables. One is going to be mx radius. The other is going to be my radius. This may represent the radiuses for our oval here. For example, the x radius might be something like this. The y radius might be something like this. And this is how we're going to be representing this shape here. We also have a draw method which is going to print the information about this shape here. It is going to say the description that we're going to be inheriting publicly from shape, but it is also going to say the radius information for this shape. It is going to give us the x radius and the y radius here. And we have a bunch of constructors here. We have a default constructor, which is really not going to do anything. We also have a constructor that is going to be taking two parameters to forward the data in our member variables here. This is the kind of class we're going to set up in our program. We also have another derived class from oval, and this is going to be a circle class. It is going to be a specialization on oval in which both x and y radius are equal. So the x radius is going to be something like this, and the y radius is going to be something like this. And both of these are going to be equal. So this is going to give us a circle shape. We also have a draw method, which is going to print the description and the radius. We can really pick any radius. We can pick the x radius. We can pick the y radius. They are really going to be the same because they are equal for our circle shape. We also have a simple constructor, which is going to take the radius, and we are going to be using this radius to forward the data to our oval part of us, and we're going to be setting this as both x and y radius. This is the setup we have here. Okay, now that we have our inheritance hierarchy, we're going to try and use it and really explore the idea of static binding in C++ inheritance hierarchies. So here we are trying to create simple objects of our classes. We have a shape object, we have an oval object, and we have a circle object. we are going to go through a base pointer and try to manage our objects here. In our first line, we're going to set up a shape pointer and we're going to store in the address of shape1. And what we would want in our C++ program is that if we call the draw method on this shape pointer, we would want the shape draw method to be called because we have a shape object stored in our base pointer here, or in other words, we are using a base pointer to manage this object in memory. Down here, we store a novel object in our shape pointer, or in other words, we're going to be using this base pointer to manage an actual oval object in memory. And the setup we want is that if we call the draw method on this shape pointer now, we are going to get the oval draw method to be called. This is the setup we want. And down here we have another example where we are using this base pointer to manage a circle object. We are going to store the address of the circle object in this base pointer. This is how we do this. And when we call a draw method on this base pointer, we want the circle draw method to be called. So with polymorphism, what we really want is to call a method on the base pointer and get the most specific possible method called on our pointer. This is the setup we want. But this is not what we get by default in C++. If we happen to do this and run our program as is now with the current knowledge that we have, on the first line here, we're going to get the shape draw method called. This is what we want. But on the second example here, we will see that we see the shape draw method also called. And on this line, we will also see that we get the shape draw method to be called. This is not what we want, and this is static binding. So what is happening here is the compiler is looking at the type of the pointer, and it is using that to decide which draw method to call. So the compiler is basically saying, I have a shape pointer, so I am going to call the draw method on the shape class. Down here, it is going to see that it also has a shape pointer, and it is going to call the draw method on shape. And down here, it is going to see that it has a shape pointer, and it is going to call the draw method on the shape class. This is what static binding is all about. The compiler is going to resolve the draw method statically. And what that means is that the compiler is going to look at the type of the pointer that we have, and it is going to use that to decide which draw method to call in our inheritance hierarchy. So this is the default, and it is called static binding in C++. We also get the same behavior if we try to use a base reference to manage our actual object in memory. Here we have the same kinds of objects we had in the previous slide, and we are using a base reference to manage our object. And what we really want is that if we go through a base reference to call our draw method, we will get the most specific draw method called. So if our base reference is managing a shape, we will get the shape draw method called. If our base reference is managing an oval object, we want the oval draw method to be called here. And if our base reference is managing a circle object, we want the circle draw method called here. This is what we want. But again, the compiler is just going to look at the type of the reference. So for the first line here, it's going to say, I have a shape reference, so I am going to call the shape draw method. That's what we're going to get here. On the second line here, it's going to say, I have a shape reference, so I will call the draw method of the shape class. That's what we're going to see here by default. And on this line here, it is going to say, I have a shape reference, so I am going to call the draw method on the shape class. And this is the behavior we get by default. And this is static binding in action. Okay, so now that we have seen what static binding is all about, let's re-examine the idea of why we need polymorphism. And I am going to give you a simple example here. Suppose we have a bunch of shapes we manage in our programs, and we want to draw all these shapes. If we want to draw a circle with the current setup we have, we would set up a draw circle method. If we want to draw an oval, we would need to set up a draw over method, and this will call our circle draw method, and this will call our oval draw method. This is going to do what we want. But try to think about this. If we have 100 shapes in our program, we will need to set up 100 such methods, and this is a mess. I don't think you want to do something like this. And we have another simple case that I want you to consider. Suppose we want to store all these objects in collections, and we're going to use an array to try and drive this point home here. If we want to store these guys in collections, we will need to set up different collections, because as we have it now, we can't store different types in an array. So what we would need to do now is to set up an array for circles and set up an array for ovals and do more collections for different kinds of shapes that we support in our program. And if we want to draw them, we have no choice but to set up different kinds of loops. And each of these loops is going to be looping on each of these collections here. Hopefully you can see that this is by design. We don't want to do this. We want to set up something that is really easier to manage in our program. And polymorphism in C++ was designed to exactly solve this kind of problem. What we really want in our C++ programs is to set up one draw method. For example, we can give it a base pointer, and it doesn't matter which kind of object we pass it when we call this, we will get that method to be called at runtime when we actually need to draw this shape. If we pass in a circle, this is going to draw the draw method on a circle. If we pass in an oval, it will call the draw method on our oval object. If we pass in a rectangle, for example, it is going to call the draw method on our rectangle object. This is what we want. We also want the same kind of setup if, for example, our functions are taking reference, and this is what we're going to get. This is what we want with polymorphism, and this is really going to improve on the design that we had earlier when we needed to set up a specific method for each shape, and we would end up with hundreds of draw methods, and that's really bad. It's not manageable. This is also going to solve our problem with collections. We really need to set up one collection which is going to be taking into account all the shapes that we manage in our inheritance hierarchy. So the setup we do is something like this. We're going to set up an array that is going to be storing pointers to shape, and we can store in the address of a shape, we can store in the address of an oval, we can store in the address of a circle, because if you really think about it, a circle is a shape, an oval is a shape, and a shape is a shape. So this is going to work, and when we get to loop through this collection and call the draw method, for the first item here, we will call the draw method on the shape. For the second element here, we will call the draw method on the oval object. And for the third element here, we will call the draw method on our circle object. And we will draw a shape, an oval, and a circle with just one loop. And this is really cool. This is the design we want. Now, this is not the default behavior we get in our C++ classes if we set up an inheritance hierarchy with our draw methods. What we get by default is static binding, but we will see how we can get dynamic binding or polymorphism in the next lecture. For this one, we're going to explore static binding, and we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is static binding with inheritance. We are going to grab our template files. This is going to be our starting point here. We're going to put in these files. And I am going to put in our classes to save time. If you want, you can download these classes from the attached resource section on this lecture. You're going to find them and you can use them as a starting point. This is going to save us a few seconds because we don't really want to type these classes. You already know how to create classes if you made it this far in the course. So I am going to drag this and drop here to open in Visual Studio Code. And this is going to give us a good starting point here. We have a base class, which is our shape class. It is going to have a simple member variable, which is going to be the description. One thing I think we need to improve on this is to use a string view to pass our parameter here. So let's include string view. We can include that here. We're going to say include string view because we are using modern C++, and we're going to change this to be an std string view by value. We can do this. Okay, so we have our class here and we have a draw method, which is really not going to do anything special. It's going to just print the description here, and we're going to see it printed out on the output stream. If we look at the CPP file, we just have an implementation of our constructor and we have a destructor. We're going to fix our parameter here to make it an std string view. Let's look at our ovo class. It is going to be deriving publicly from shape. And we have a bunch of member variables here, 2 to be exact. One is going to be the x radius. The other is going to be our y radius. We have a constructor here which is going to be taking 3 parameters, 2 parameters for the data for our radius here, and we have a third parameter which is going to store our description data. We're going to also change this to be std string view, and this is going to do, we have a draw method which is going to be printing the description and our radius data. And this is really it. We don't need anything fancy here. Let's look at our overall CPP file. It is going to have the implementation for our constructor and our destructor here. We just need to change the type for our description here and make this an std string view. Let's do this. And we will look at our circle class, which is going to be inheriting from ovo. Publicly, it won't have any member variable because it's just going to forward the data to the ovo part of ours. It doesn't really need to do any other specialization. But what we need is a method which is going to return the radius because we want to print that here. So we can head over in our ovo class and set up a protected section which is going to give us these methods here. So I am just going to put them in here to save on some time. It is protected because we want this to be usable in derived classes, but we don't want this usable from the outside. This is the setup we can achieve by making these guys protected here. GetXrad is going to return the x radius. GetYrad is going to return the y radius. They are a const because we don't intend for these to modify our object. And if we go in our circle class, this is going to work now. We will be able to print our information on our circle object and we will see on our output stream. If we look at the implementation of our circle class, it is nothing complicated. It is just going to take the double radius and it is going to forward the data to the ovo part of us. And our description here will need to change to take into account that we want to use std string view here. So let's change this to be std string view. We can do that. And we are going to head over in our CPP file and change that as well. std string view, we can do that. And now our classes are really complete. We can head over in our main CPP file. We can clean that up a little bit. And we're going to remove what we don't need here. We are going to include our classes, so we're going to include shape. Let's do that. We are going to put in oval. Let's do that. Oval.h. And we are going to put in circle. And we are going to create objects of these classes and try to print their information. So we're going to set up a shape called shape1. We're going to set up an oval called oval1. We're going to set up a circle called circle1. And we're going to see what kind of information we see if we try to call the draw method. Again, in shape, the draw method is just going to say that we are calling shape draw. In oval, we are going to say that we are drawing an oval, and we're going to say the description and the radius. In circle, we're going to say that we are calling the draw method on the circle object and say the description and the radius here. This is the information we want. So we are going to try and build this program using GCC, our favorite compiler. You can really use any compiler you have your hands on, but we are going to use GCC here because it is our favorite. And we're going to have a bunch of errors. What it is that we have here? What is it that we have here? Let's go in shape header at line 4 and see what we have. And we have a J here that we don't want. Let's take this out and we're going to build again. We're going to pass this through GCC. And the build is going to be good. We can bring up a PowerShell window to run our program. Let's run Rooster. And we're going to see that shape draw was called drawing shape 1. You see, we have just created shape 1 here and we are printing its information. We are going to call the oval draw method and we're going to print The information on that, you see that it is over 1 here. And we're going to put out our radius data. X radius is going to be 2 as we specified here. Y radius is going to be 3.5, and this is our information. We are also going to call the draw method on our circle object. This is what we get. And we're going to say we are drawing circle 1 and the radius is going to be 3. This is our information here. But we don't want to go through direct objects to manage our data here. What we want is to either go through base pointers or base references. So we are going to set up a shape pointer. Let's do that. We're going to say shape because that's our base class. And we're going to say shape PTR to represent our pointer. And we're going to store in the address of shape1. We can do something like this. And to really see what is happening, we're going to comment out our calls to draw method here. And we're going to see what happens. So if we say shape PTR and call the draw method, we can do that. Let's try and build our program. We're going to pass this through GCC. You're going to see that it is going to work and it is going to do what we expect if we run this program here. You can clear and run roster. We're going to see that shape draw was called and we are going to be drawing shape 1 here. This is what we expect. But if we go down and say we don't want to call the draw method here, we are going to store in, let's say shape PTR, and we're going to store in the address of our over1 object. And we want to call the draw method here. Now, if you do this, as we saw in the slides, what we really want is to get the draw method on our actual oval object called. And if we were, for example, drawing things on the screen, we would draw an oval. This is what we want here. But this is not what we're going to get. You're going to see that we still get the draw method from the shape class called, and it is going to say drawing over1. Let's try and build this program, and I really want you to see this. So the build is good. We can clear and run roster. You're going to see shape draw, even if we are storing again a novel object. So this is the default behavior we get, and this is static binding that we get by default in our inheritance hierarchies. So what the compiler is really going to do here, it's going to look at the type of the pointer that we have here. It is going to say, I have a shape pointer, so I am going to call the draw method on the shape type that I have in my pointer here. And we are going to see that this is calling the draw method on our shape. And this is not what we want in most cases. We are going to see that we get the same behavior if we store in a circle object. Let's do that. We're going to say shape pointer, and we're going to store in the address of our circle 1. And then we're going to call our draw method on our shape pointer. Again, this is going to draw a shape. It's not going to draw a circle that we really are managing with our base pointer here. And some of you must be thinking, why are we able to store circle pointers, for example, in a shape? Well, a circle is a shape according to our inheritance hierarchy. If we take a closer look again here, you're going to see that oval is going to be inheriting from shape, and a circle is going to be inheriting from oval. So from what we learned in the last chapter, oval has a shape part in it, and circle has an oval part in it, which in turn is going to have a shape part in it. So from this understanding, it shouldn't really be surprising that we are able to manage a novel object with a shape pointer, or the fact that we are able to manage a circle object using a shape pointer. This is why we are able to do something like this. Okay, so I hope this is super clear. But again, we are not getting the default behavior that we want, but we will see how we can achieve that in the next lecture. For now, I really want you to understand what static binding is all about. And it is the fact that the compiler is going to look at the type of the pointer here and use that to decide which method it is going to be calling in our inheritance hierarchy. The compiler, for example, is going to see that we have a circle object stored n at line 25 here, but when it wants to decide which draw version to call, it is going to look at the type of this pointer here, and it is going to use that to decide which draw method to call. And in this case, it is going to call the shape version because the type of this pointer is shape. Okay, so I really hope this is super clear here. We are going to get the same behavior if we try to manage our objects using references. For example, if we go through a shape reference, let's do that. We're going to say shape reference and say shape ref. And we are going to store in shape1, for example. Let's do that. And we want to call the draw method on shape reference. Let's do that. So let's call the draw method. And you're going to see that we will get the shape method called. And this is really making sense because we have a shape object managed by this reference here. So if we build our program, let's do that. We're going to pass this through GCC. You're going to see that we get what we expect. The build is going to be good. We're going to clear and run Rooster, and we see shape draw called. This is what we want. But if we use this reference to manage a derived object, for example, let's put in oval1, we can do that. We're going to see that we don't get the most specific draw method for oval here called. We will still get the method for shape called. Let's build and show you this. This is static binding again. Okay, the build is good. We can clear and run Rooster. We're going to see that shape draw, it is drawing. We don't get the oval draw method called. We get shape draw method. Again, the compiler is going to look at the type of this reference by default, and it is going to use that to decide which draw method to call. If we even put in a circle, we are going to get the same behavior. Let's build with GCC. The build is good. We can clear and run Rooster. We see that shape draw is called, and this is really not what we want. Okay, so this is static binding, and it is the default behavior we get if we have an inheritance hierarchy with the same method spread across each derived class. We're going to get the shape version called, even if what we are really managing with a shape pointer or a shape reference is a derived object. I really want you to understand this. Now, let's see why this is really bad design by default in C++. If we happen to need to pass shape parameters to functions, for example, we might do something like this. We might need a function to draw a circle. We might need a function to draw an oval. And if you happen to have 100 objects you can draw in your program, you have no choice but to set up 100 drawing methods or functions. This is really bad design. You don't want to do something like this. So what you would do in your program, for example, is go down and say drawing. And you would say, for example, draw circle and pass in a circle and say draw oval. Do we have a draw oval function? Let's see. Yes, we have that. We can go down and say draw oval and pass in our oval one. This is going to work just fine, but hopefully you can see that this is bad design. If you have a lot of shapes in your program, this is going to quickly become unmanageable, and you don't want to do something like this. What we want is to be able to only have one method and get the C++ runtime to resolve which one is called at runtime when we get to pass our actual objects, and we will only have one function which is going to take into account hundreds of shapes that we might potentially have in our C++ program. This is going to be much easier to manage, and we will actually be able to achieve this in the next lecture, so stay tuned for that. Another problem with this is if you happen to need to store these shapes in collections. If you need to set up something like this, you will have no choice but to set up different collections for each type. For example, we might set up a collection for circle, a collection for oval, and here we are just using arrays to model our collections. And this is really bad design. If you happen to have 100 shapes in your program, you will set up 100 such collections. And the only difference is that they are just different types. And this is really bad design because even if they are different types, they are related and they are all shapes in our C++ program. And what we really want is to set up one collection which is going to take into account all these kinds of shapes that we might have in our C++ program. And we will be able to achieve this again in the next lecture. But the whole point of this lecture was to show you static binding that we get by default with our inheritance hierarchies. Static binding may be bad if you really are managing a lot of related objects in your C++ program. And all these objects have the same method that each derived class is specializing, but you want the most specialized method to be called on the actual object that you are managing with a base pointer or a base reference. Hopefully this is super clear. I apologize, this lecture turned out to be really long, but I wanted you to make this super clear, and everything else we do in the remainder of this chapter is really going to fall in place. So make sure you understand this, and if you have a problem, do ask me. I will do the best I can to help you out. This is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to show you how you can achieve dynamic binding using virtual functions in C++. Go ahead and finish up here and meet me there. In this lecture, we're going to see how we can achieve dynamic binding or polymorphism using virtual functions in our inheritance hierarchies. In the last lecture, we had a hierarchy like this, where the base class was shape. We had an ovo class which was publicly deriving or inheriting from shape, and we had a circle class which was publicly inheriting from ovo. And the problem we had was that if we happen to be managing oval or circle objects using shape pointers or shape references, we don't get the correct methods called if we call the draw method on our base pointer or base reference. And this was really bad, and this is something we want in practical C++ programs. I am here to tell you in this lecture that you can just achieve that by doing a tiny modification on your inheritance hierarchy. All you need to do is to mark the methods you need to be dynamically resolved virtual. And we do that by inserting this virtual keyword in front of our function. So we're going to do that on our shape class, we're going to do that on our oval class, and we're going to do that on our circle class. Once we do this, the C++ compiler is going to know I want to be looking at the type of the pointer or reference to know which kind of method to call in my inheritance hierarchy if I happen to be using a base pointer or a base reference to manage a derived object. And we're going to be making this super clear in a minute. And if you are lost, please bear with me, you're going to understand. So let's do this. We're going to modify our shape class and change our draw method to be virtual. As you see here, we're going to head over in our oval class. We're going to modify our draw method and mark it to be virtual using the virtual keyword here. And we're going to move in our circle class and change it to be virtual as you see down here. This is really all we need to do from what we had in the last lecture. And this is going to be magic. Let's look at what we can achieve now. We're going to set up 3 objects, shape, oval, and circle, as you see here. And we're going to be calling our method, which is going to be taking references, and we're going to see that we get the correct, most specific method called. So for example, here we will call the shape draw. Down here we will call the oval draw method because we just passed in an oval object. And on the third line here, we will get the circle draw method called, and we will see it printed out on the console. This is really cool. This is what we want to achieve. If we want to call our methods that take pointers, we can do that. And on the first line here, we will call shape draw. On the second line here, we will call oval draw, and on the third line here, we will call circle draw. This is what we want to achieve. And if we happen to be setting up a row base pointer like we do here and storing a derived object like this, or another way to say this, if we happen to be using this base pointer to manage a derived object and we call the draw method on the base pointer, the compiler is going to know that it will need to resolve this draw method dynamically. The reason is, this is a virtual method, and if a method is virtual, the compiler won't do static binding like we did in the last lecture. The compiler is going to be doing dynamic binding. And with dynamic binding, the compiler is not going to look at the type of the pointer, it is going to look at the type of the actual object that the pointer is managing, and this is going to give us the behavior that we wanted starting from the last lecture. Okay, now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is polymorphism with virtual functions. We are going to be reusing the code from the last lecture because that's going to give us everything we want. We will leave out the binary file here, which is Rooster, and we're going to copy everything we want. We're going to put that in the current project, and we're going to open this in Visual Studio Code. We are going to have our main CPP file with a bunch of methods here, and we will just need to modify this a little bit to achieve dynamic binding. As we saw in the slides, all we need to do is to mark all these draw methods as virtual. So we're going to say virtual void draw in the shape class. We're going to go in the oval class and do that. We're going to mark our method as virtual. And we are going to go in our circle class and mark our draw method as virtual. Let's do that. And the moment we do this, we're going to get dynamic binding behavior in our inheritance hierarchy here. And this is really cool. So let's go back and try to play with what we had before. I am going to comment out everything we had, and we're going to be doing things in step here. Let's go through the code that uses base pointers because that's where we started out from in the last lecture. And we are going to mark that here. Let's put in some space to make it easy to follow. So we are going to uncomment the line here that calls the draw method when we have a shape object stored in our base pointer, or when we are using a base pointer to manage a shape object here. We can also comment out all these lines because we don't want this to do anything. And let's see. Yes, this is what we want. We are setting up our shapes, and we are using a base pointer to manage an actual shape object. And if we call the draw method, we expect this to call shape draw. And this is what we're going to get. Let's build our program. We're going to pass this through GCC, our favorite compiler. The build is going to be good. We can bring up a PowerShell window we can use to play with us. If we call Rooster, we're going to see that shape draw is called, and we are drawing shape 1. Now, if we change this to manage an actual oval object, we can do that. We can do that through this line here, and we expect this to